Please welcome Chief Executive Officer of the American Physical Society, Jonathan Bagger.
Well, thank you, and good afternoon. So today's Kavli Foundation Special Symposium brings together perspectives on quantum science and technology at a moment that the field is both moving quickly and at the same time developing a better understanding of what is necessary for quantum to deliver on its promise. Quantum research is moving from isolated demonstrations towards more integrated systems, and the conversation is sharpening along with it. Because we're not asking not only what is possible in principle, but also what can scale, what it will cost in terms of workforce, manufacturing, and long-term investment, and what APS can do to help. So as we proceed, it's important to remember, though, that quantum science does not stand apart from the rest of physics. It draws upon decades of work in condensed matter, atomic and optical physics, material science, and engineering. And its future will depend on a sustained and deep collaboration across academia, industry, and national labs, along with thoughtful engagement of society. So in this symposium, Bridging a Shared Future for Physics and Humanity, this symposium spans the full arc from fundamental insight to real-world impact. And we're extremely grateful to the Kavli Foundation for making the session possible. For more than 20 years, the Kavli Foundation has shared the APS mission to advance science for the benefit of humanity. Their support has enabled us to bring you a diverse array of speakers to discuss the many contributions of physics to our understanding of the universe and our place in it. And so it is now my pleasure to introduce our session chair, Nitin Samarth. Nitin is the Vern M. Willman Professor of Physics and Professor of Materials Science and Engineering at Penn State University and Chair of the March Meeting Program Committee for this year's summit. Nitin is recognized for his pioneering work in semiconductor and topological spintronics, where his research on thin films and nanostructured materials has helped reveal new quantum and magnetic phenomena and advance the development of spin-based electronic systems. He is the author of more than 200 scientific publications and a fellow of both APS and the American Association for the Advancement of Science. And in 2024, he was honored with the APS David Adler Lectureship Award. Nitin, welcome, over to you.
Thank you, Jonathan. So as co-chair of the APS Global Summit, it's been a real privilege and honor to arrange this year's March Kavli Symposium. I would like to first of all thank the Kavli Foundation for the support that they provide. This is an enormous impact that they have, when they allow us to attract such stellar speakers to give you an idea of the state of the art in particular fields. What I'm going to do first in a few minutes is just sort of give you the general arc of what's going to be happening during this symposium. In keeping with our meeting's theme of a shared future for physics, you'll hear from our speakers about frontier advances in quantum science and technology and how these advances might have an impact across scientific boundaries within physics, but also impact our society at large. So I'm going to give you a brief overview of what the speakers generally are going to be talking about. Our first speaker, Professor John Preskill from Caltech, will give you insights into the foundations of the second quantum revolution, as many of us refer to it, which is well underway now, and the challenges and implications of realizing true quantum advantage. The second speaker, Professor Michelle Simmons from the University of New South Wales in Australia. Thanks, Michelle, for taking a long trip for this talk. Very appreciative of that. will talk about the impressive atomic scale engineering of spin qubits in semiconductors. And I particularly want to emphasize that the project she's going to talk about is an excellent example of how long-range, consistent, dedicated government funding can make a big impact to take something from, an idealized vision to translational impact. And I think you'll get a sense of that in her talk. Our third speaker, Professor Ramamoorthy Ramesh from Berkeley, refers to himself as an aberration in this symposium. He's there with a purpose. And he will talk about the critical role that quantum materials will play in solving important challenges in conventional computing, particularly in the age of AI, where we are all faced with these energy-hungry machines trying to do our bidding, or perhaps we'll end up doing their bidding, I don't know. He's going to give you a sense of the challenges that the opportunities really, that quantum materials provide, right? After that, we're going to take a little bit of a diversion, but into something really important. When you make interesting quantum materials, you need to develop techniques and probes that are appropriate for learning about those quantum materials. So you'll learn from Professor Margaret Murnane from University of Colorado about how one can harness state-of-the-art advances in laser physics to probe and sculpt quantum materials of the future. And last but not least, we'll hear from David Awschalom from the University of Chicago, from the Preskill School of Molecular Engineering, about how pioneering advances in quantum science that are carried out by our students and postdocs in the world of academia. So how do you go from the academy and really make impact, in the broader society, particularly with respect to translational impact in industry? And I think you'll hear the full arc of how that can be effectively done. So that said, I'm going to now start introducing the speakers as they come up. It'll be first Professor John Preskill, who's the Richard P. Feynman Professor of Theoretical Physics at Caltech, and he's also director of the Institute for Quantum Information and Matter at Caltech. Now, given the 36-minute kind of typical timeline, I'm not going to spend too much time going into all the honors and awards and everything of all the speakers and give you a full biography. But let me just mention that he started out with making influential contributions to particle physics and cosmology, and now is really one of the leaders in theoretical aspects of quantum information science and quantum computing. And at a very personal note, I'm very happy to say that the online lectures that John Preskill has provided for the broader community make an enormous impact. So for example, for the undergraduate Introduction to Quantum Information Science course that I teach, I know that the students have just truly loved these spectacular lectures. So without further ado, John, it's your turn to take the stage.
Well, thanks very much for the kind introduction. I'm honored to be here with the other esteemed colleagues on this program to tell you about the ongoing quest for quantum advantage. For transparency, I'd like to note that alongside my Caltech role, I'm also involved in a recently launched company, or Atomic, which is developing neutral atom quantum technologies related to some of the ideas I'll discuss today. I was drawn into quantum information science in the 1990s. That was an exciting time. The efficient algorithms for factoring and computing discrete logarithms were discovered, followed soon after by the first quantum error correcting codes and the formulation of the principles of fault-tolerant quantum computing. So by late 1996, many of us appreciated that powerful quantum computers that can solve hard problems would eventually be built and operated, though the timescale was highly uncertain. And now is also an exciting time. We have now quantum devices of sufficient scale and accuracy that they can perform some tasks which are beyond the reach of our conventional computers. Error correction, which had been a playground for theorists, is now something that can be executed and perfected on actual devices. And the world is investing heavily in developing quantum technology, and that's helping to accelerate progress. The impact on physics is evident at the APS Global Physics Summit. The APS division of quantum information is still growing rapidly. With more than 4,000 members, it's now the second largest of the APS units. And the membership is more than half students, as has been the case since this group was founded 20 years ago. In fact, this year is the first time that there were more abstracts submitted to the March meeting from DQI than from any APS unit. Well, most of us are physicists. I'm a physicist. And I felt, since I first got into this field, that quantum information is an opportunity to explore the foundations of physics. It's a frontier of the physical sciences. Different in some ways than the short-distance frontier of particle physics and the long-distance frontier of cosmology that I worked on earlier in my career. But like those, very fundamental and exciting. We are acquiring and perfecting the ability to create and precisely control very complex states of matter, states of many particles that are so highly entangled, so complex, that we can't simulate them with our most powerful conventional computers or predict how they'll behave with existing theoretical tools, and that opens opportunities for new discoveries. And our confidence that that frontier is fruitful to explore rests largely on the concept of quantum entanglement. That's the word we use for the characteristic correlations among parts of a quantum system that are different from the correlations in the classical world. You can think of it this way. We might imagine a book which is 100 pages long, and if it's a classical book written in bits, every time you read another page, you acquire 1% of the information content of the book, and after you've read all the pages one at a time, you know everything that's in the book. But suppose instead it's a quantum book written in qubits, where the pages are highly entangled with one another. Then each time you look at a page, you see only random gibberish. And even after you've looked at all of the pages one by one, you still know very little of the information content of the book. And that's because in the quantum book, the information isn't encoded in individual pages. It's carried almost entirely by the correlations among the pages. So if you want to read the information in the book, you need to make a collective observation on many pages at once. That's the essence of quantum entanglement, very different from notions of correlation we encounter in everyday life. And part of what's so intriguing is that these correlations among quantum systems are extremely complex to describe in ordinary language, the language that we understand and that our computers understand, so that if you wanted to express very precisely all the correlations among the qubits in a system of just a few hundred in terms of ordinary bits, you would need more bits than the number of atoms in the visible universe. Now that in itself doesn't tell us that manipulating complex quantum systems can be useful, but we do have reasons to think quantum computing is going to be powerful. First of all, because we know of some computational problems which we strongly believe are hard to solve for conventional computers, where at least theoretically a quantum computer can find the solution efficiently. But more tellingly, we just don't know how to simulate what a quantum computer does in general efficiently using a conventional computer. One way of thinking about how a quantum computation proceeds is that it's able to follow in parallel many computational paths from the input to the output. And in a quantum algorithm, what we strive for is for the amplitudes associated with those different paths that end at the right answer to constructively interfere, and for the amplitudes associated with paths that arrive at the wrong answer to nearly cancel one another out. So when you measure the output, you see the right answer with high probability. And we know how to arrange that for some problems that have appropriate structure, but there are a lot of problems for which we don't know how to dramatically speed up the time to solution using a quantum computer. But it's an intriguing fact that there are problems that we think cannot be solved efficiently with classical computers, but can be with quantum computers. So it's a compelling question to understand what are these problems that are classically hard and quantumly easy. And I think we've learned a lot about that over the last 30 years. I think we have a lot more to learn about that. But if you're a physicist, there's a natural place to look, because we expect that with quantum computers, we'd be able to efficiently simulate any process that occurs in nature. And we don't think that's true of conventional computers, which can't efficiently simulate very highly entangled matter. So with quantum computers, we expect to be able to go further in exploring properties of complex molecules and exotic materials, and also to explore fundamental physics in new ways, for example, by simulating high-energy collisions of fundamental particles, or the quantum behavior of a black hole, or what happened in the universe right after the Big Bang. Now, of course, if we're going to build a quantum computer, the qubits have to be instantiated in some physical system. And there are a number of approaches to building quantum hardware platforms which are advancing in parallel. And it's important for now that we continue to support the advance of these various modalities, because we don't understand clearly yet which technology will have the most impact in the long run. It could be hybrids of different technologies that are best suited for some tasks, or different technologies might have their own niches, the problems for which they're especially well suited. And we should remember that the quantum technologies that are advancing impressively now are built on curiosity-driven fundamental research from decades ago. A case in point is this year's Nobel Prize, recognizing research on macroscopic quantum mechanics in the 1980s, which provided the foundation for the superconducting processors that are being widely used today. And we can expect that in the future, as in the past, curiosity-driven fundamental research will give rise to new ideas and technologies which will be useful to society in the future. Now, the idea that quantum computers could have important applications is quite old, goes back arguably 45 years. And we're just now getting to the point where quantum computers are capable of doing some interesting things. So evidently quantum computing is hard to do. It's hard because in a quantum platform, we want to simultaneously satisfy some criteria which are hard to reconcile. We want the qubits to interact strongly with one another so we can rapidly process the information that they encode. We don't want qubits to interact with their environment, which could cause a quantum computation to fail. But we do want to be able to control our device from the outside and eventually measure it to read out the result to a hard computational problem. And it's taken decades of technical advancements to get to the point we are now, where these criteria can be simultaneously realized, at least to some degree, in actual devices. The reason it's so important that the quantum computer not interact with its environment is because of the phenomenon we call decoherence, which stems from a fundamental difference between quantum and classical information, namely that you can't observe a quantum system without disturbing it in some uncontrollable way. And if the information leaks to the environment where it, in principle, could be observed, even if we don't observe it ourselves, that's just as bad. So when we're processing information in a quantum computer, we need to keep it almost perfectly isolated from the outside world. And that's hard to do because our hardware is far from perfect. But we've understood in principle how it can be done using the principles of quantum error correction. The essence of the idea is that if we want to protect quantum information from damage, then we should encode it in a very highly entangled form. So when the environment interacts with parts of our system one by one, it can't access the encoded information and therefore need not irreversibly damage it. And we've understood, at least theoretically, how to efficiently process information that's encoded in that very highly entangled form. So where are we now? The quantum technology that exists now is sometimes called NISQ, meaning noisy intermediate scale quantum. It's a technology that allows us to perform quantum computations with thousands of 2-qubit operations and read out a useful signal. And that's becoming useful for scientific exploration, but so far has limited commercial value. And what we aspire to is fault-tolerant application scale quantum, or FASC machines, which would unlock a variety of scientific and commercial applications by performing billions or trillions of 2-qubit operations. But that means we have to reduce error rates in quantum hardware by many orders of magnitude, and the only realistic way we can foresee doing that is by using quantum error correction to cover the chasm between NISQ and FASC technology. So there's progress in a number of directions. I'd like to highlight in particular that we can now do simulations of quantum dynamics with quantum devices in a regime that arguably is classically hard. We're seeing superconducting and atomic processors advancing impressively. And theoretically, if we can build devices which have long-range connectivity, we found that that can greatly reduce the overhead cost of quantum error correction. For quantum scientists, it's becoming increasingly interesting to run simulations on the existing quantum platforms. We have superconducting systems with over 100 qubits and 2-qubit gate error rates that are approaching 1 part in 1,000. The ion trap processors have even higher 2-qubit fidelities and also all-to-all connectivity. There are neutral atom processors with the atoms trapped in optical tweezers with hundreds of qubits. 2-qubit gate fidelities are lagging somewhat behind, but they're rapidly improving. So users face trade-offs. The improved fidelity and the non-local connectivity offered by ion traps, for example, comes with a significantly slower clock speed than superconducting processors. And that means we can't run a quantum computation as many times and achieve as high statistical accuracy in estimating expectations of output observables. Simulations of fermions are especially compelling because electronic structure underlies chemistry and materials science. These simulations are hard to do, particularly if we're interested in studying dynamics in systems in more than one dimension. The Fermi-Hubbard model is a caricature of the materials that exhibit high-temperature superconductivity, which has been much studied in recent decades. And in the past year, we've seen simulations of Fermi-Hubbard dynamics, so far on systems with a 6x6 lattice, requiring altogether 72 qubits. That's already beyond the reach of exact classical simulation. You can compare to various classical heuristic algorithms for simulating the dynamics and find discrepancies. And one can argue that in this regime, it's actually the quantum device which is producing more trustworthy results. I should mention that we have analog simulators for Fermi-Hubbard physics based on neutral fermionic atoms in optical lattices with thousands of sites. But with the digital quantum processors, we have greater flexibility in the initial states we can prepare, the output observables we can measure, and the Hamiltonians we can reach. Now, we would like to increase the system sizes for such simulations, and as NIST technology improves, we'll be able to do so somewhat. But eventually, we'll have to cross over to fault-tolerant operation if we want significantly lower error rates, which will allow simulation of larger systems. So then we face the unpleasant fact that there's a very hefty overhead cost for doing quantum error correction. You can see how it goes by considering the surface code, which has been much studied because it has two big advantages. One, it can tolerate relatively high 2-qubit error rates. And secondly, it only requires local processing in a two-dimensional layout, which is convenient for solid-state platforms. The surface code encodes a single logical qubit in a square array of data qubits, which are interspersed with check qubits. Each check qubit interacts with its four neighbors to produce a bit of syndrome information for diagnosing errors. And after collecting syndrome information for many successive rounds, you can then decode the results to infer what errors occurred and what needs to be done to correct the errors. The surface code has a threshold of accuracy of about 1%. That means that when the physical two-qubit error rates are below that 1% level, as you increase the size of the array, which we call the distance of the code, a measure of its error-correcting power, the logical error rates decay exponentially as the distance increases. But if we make the plausible assumption that we can do two-qubit gates with an error rate of 1 part in 1,000, if we would like to be able to perform computations with, say, billions of gates and have correspondingly low logical error rates, then the number of physical qubits, both the data qubits and the check qubits needed to protect a single logical qubit, can approach 1,000. And if we want to do a simulation on thousands of logical qubits, then the physical qubit count goes into the millions, which is quite daunting from the perspective of the current technology where we have hundreds of physical qubits. You can appreciate the state of the art from a demonstration done by the Google Quantum AI team in 2024. On a superconducting processor, they perform millions of rounds of surface code syndrome measurement, each taking about a microsecond. And they extracted from those calculations an important parameter they call lambda. That's the amount by which the logical error rates decay when the distance of the code increases from 3 to 5 and then from 5 to 7. They found lambda of about 2, indicating that the error rates would continue to decline as the system grows in size. Looking ahead, as these processors improve, we can expect to see better values of lambda, larger codes, and eventually high-fidelity logical two-qubit gates protected by error correction, which are much more accurate than the physical two-qubit gates themselves. But what about that very high overhead cost? Can we do something about it? Well, theoretically, we can make it a lot better if we're not limited to geometrically local processing. In quantum low-density parity check codes, the check qubits each interact with just a few of the data qubits, but now the data qubits are not required to be in close proximity to one another. It turns out that that means that we can achieve a given distance with fewer checks than we can in the geometrically local setting. Fewer checks means fewer constraints on the data. That means more logical qubits. So it turns out that if you're trying to reach a certain distance with a certain number of physical qubits, you can do that while encoding many more logical qubits in a non-local quantum low-density parity check code than you can in the surface code. The improvement could be orders of magnitude. More logical qubits means less overhead cost for quantum error correction. Now, the type of non-local connectivity that we need to enable these high-rate quantum error-correcting codes could in principle be achieved in solid-state devices, but that might require complex fabrication. It's more natural in a setting where the qubits are movable. For example, the movable atomic qubits in ion traps where atoms can be shuttled electromagnetically, or the neutral atom processors where the atoms are held by optical tweezers and the tweezers can be reconfigured optically to change the position of the atoms. So now, because they're not restricted to just interacting with their neighbors in a fixed geometry, we get some of the advantages that high-rate codes can offer. There's been a lot of theoretical work in the last few years confirming that we can get much higher encoding rates taking advantage of this kind of non-local connectivity, and that we can still have high accuracy thresholds and feasible decoding as in the surface code. And in just the last year or two, there's been quite a lot of progress in understanding how to build gadgets in a quantum computer that can perform a universal set of gates acting on these high-rate codes to lower the overhead cost of fault-tolerant quantum computing. Now, these atomic processors have a slow clock speed because of the time required for atomic movement and for readout compared to superconducting processors, but that slow clock speed can be partially compensated by these much higher decoding rates, encoding rates. And in fact, now in the case of the neutral atom processors, architectures for fault-tolerant quantum computing have been demonstrated. Below error threshold behavior has been achieved. And there are trapping arrays with thousands of atoms trapped in optical tweezers. And there's a lot of work to do to turn this into a working quantum computing system, but efforts are underway to build neutral atom atomic processors with thousands of physical qubits, potentially with hundreds of logical qubits. Now, coming back to applications, we're interested not just in dynamics, but also in probing the properties of equilibrium states of matter, like ground states or low temperature thermal states. And in the last few years, efficient quantum algorithms have been developed that can simulate natural cooling processes. So the quantum system quickly finds a local minimum of the energy. And encouragingly, it's been shown under natural assumptions that this problem of finding properties of a local minimum in a quantum system is something we can do easily with quantum computers, but in the worst case, it's hard for conventional computers. So this is an arena in which we can make a rigorous statement about quantum advantage. And these cooling algorithms have been much simplified in the last year or two, so we might be able to run them on relatively near-term fault-tolerant processors. But what's not very clear is how to translate that worst-case classical hardness into a practical quantum advantage. For many physical systems of interest, classical heuristic algorithms are used very successfully to understand the properties. And it's an important but challenging task to understand more what are the physically relevant physical systems for which quantum computing has a significant advantage over the classical methods. In thinking about quantum simulation of many particle systems, a nagging question is, will AI eat quantum's lunch? There's understandably a lot of interest in using artificial intelligence to study many particle quantum systems, and that's quite promising. So where does that leave quantum computing? An opportunity for advantage in that problem space. This is part of the broader issue of classical algorithms are good and they're getting better, and classical processors are getting more powerful. What does that tell us for quantum advantage? Well, at least at this point, classical AI is hampered by a paucity of training data in the strongly correlated regime. So we can expect that quantum computers, by providing large quantity of data about how many particle quantum systems behave, can provide useful training data that classical AI will be able to generalize from to make new predictions about materials and chemical compounds. And in fact, we can show rigorously that a classical artificial intelligence system, when provided with data from quantum experiments, can make efficient predictions that would not be possible if that classical system did not have access to that quantum data. There's a lot of interest also in whether quantum computers can speed up tasks that involve large amounts of classical data. But what has been challenging is that the time it takes to load a lot of classical data into the quantum processor, and limitations on how much classical data we can read out by measuring the output tend to nullify the potential advantage from fast quantum processor. But in work that will soon appear, led by Caltech graduate student Haiming Zhao and guided by the vision of Robert Wan, We've shown that for machine learning tasks like classification and dimension reduction, there's an exponential quantum advantage not in the runtime, but in the memory requirements. That if we're trying to perform a task on a dimension and a classical data set, that a system that has a size, if it's a quantum system, which is just polylog n, can perform the task, but a classical system, in order to match the quantum system's performance, would have to be exponentially larger or would require a number of samples or an amount of processing time that's a super polynomial in n. This achievement is, this advantage is achieved in a streaming setting where the quantum system is able to query classical data in superposition when provided only with classical samples. And if we combine this with the idea of classical shadows, we can use the algorithm to obtain a very succinct classical model of the large classical data set, which provably could not be obtained without the use of quantum technology. So we're hopeful this will have practical advantages, since today's classical systems dealing with very large data sets do run into limitations coming from the size of the classical memory. So the open questions that we've been struggling with in quantum computing were already asked decades ago. How are we going to scale up to quantum systems that can really solve hard problems? And once we do so, what will be the most important applications for science and for industry? We still don't have the definitive answers to these questions. I do feel confident that in the next couple of years, it's going to be quite exciting. We're going to see quite encouraging progress towards scalable, fault-tolerant quantum computing, and that scientific insights enabled by our programmable quantum simulators will be arriving at an accelerating pace. But what about the longer term? I was intrigued by this letter that John von Neumann wrote in 1945 when he was arguing for the development of fast electronic computers. And he delineated some applications, but then said, uses which are not easily predictable now are likely to be the most important ones. These constitute the most surprising and furthest going extension of our present sphere of action. Not even a genius like von Neumann could foresee the digital revolution that lay ahead. And I think in trying to predict the future course of quantum technology, our task is even more hopeless because it's an even bigger departure from the technology we've had in the past. So it's a natural thing to say that there's a world of quantum advantage which extends far beyond what we have or can rigorously establish in advance. We were writing a perspective article, and Robert Hwan wanted to make this into a more precise statement, so he proved a theorem which, stated informally, says that predicting quantum advantage is classically hard. So suppose there's a quantum computation and you would like to know whether a classical heuristic can correctly predict the output of the quantum computer. If you have the quantum computer, you can run the computation to check. If you don't have the quantum computer, then the argument shows under natural assumptions that no efficient classical computation can predict the answer. So this reinforces the idea that there are quantum advantages which we don't yet know about, but which we will discover when we experiment with our quantum machines. So if we think about the long term, we're hampered by our limited imaginations. We might characterize the first 100 years of quantum mechanics by saying that we've had great success understanding the relatively simple behavior of weakly correlated particles like electrons and photons, and that has had inestimable scientific and technological value. The big challenge and opportunity for the next 100 years is arriving at a comparable understanding of the behavior of very highly entangled systems that are beyond what our conventional computers can simulate, and to make use of that knowledge for the benefit of humanity. I think it's reasonable to expect that the second century of quantum mechanics will produce even greater surprises than the first century did. So we should express our gratitude to the quantum pioneers of that first century of quantum mechanics, and wish good fortune to you, the quantum explorers of the future. Thanks very much for listening.
Thank you. Thank you, John, for that really clear and fantastic talk. Very inspiring, too. We have a couple of microphones which are located way up front on each aisle. So if you have any questions, please come up to the microphones, and I'll alternate between the two microphones. Yes.
Thank you very much for a very nice talk. I was an astrophysicist too, so my question is the following. You show up a lot of potentiality in terms of problems, and you underline the fact that different technology could be more suitable to tackle or attack different problems. My question is, do you see any limit in the quantum computers technology?
Do I see any what?
Any limit, something that we cannot do, or is too open question. Any limit, something that we cannot do, or problem that we cannot solve.
Any limits?
Any limits.
Any limits?
Right.
Well, yeah, I mean, actually, we have a lot of results saying that under assumptions that are widely believed, there are some tasks that quantum computers can't do much better than classical computers. In particular, many hard optimization problems are in the category that we call NP-complete or NP-hard. And for the worst, the hardest instances of the NP problems, the problems for which we can efficiently verify the solution with a classical computer, we don't think there are super polynomial speedups that will be provided by quantum computers. And that's why we need to be very thoughtful about identifying where quantum advantage can appear and be useful.
Thank you.
So there's a question online. The question asks, how is topological quantum error correction used or applied in today's research, and how promising do you think it is to reach FASC?
Okay, so the question is about topological quantum computing, which is a way of incorporating the protection against error into the hardware itself, or at least reducing the, making easier the job that software that implements quantum error correction on top of the hardware has to do. In other words, to make the gate error rate substantially better. To a theorist like me, this is a very beautiful and compelling idea. It may well be that quantum technologies sufficiently far in the future will heavily take advantage of this idea. So far, progress has been slow. The idea of a topological quantum computer was proposed actually in 1997, and efforts have been made, especially by Microsoft, to advance the technology. And I expect it will eventually work, but so far we, haven't seen the low error rates at the physical level in topologically protected devices. I hope we will. But some of the theoretical ideas related to topological quantum computing are very current because the error-correcting codes that are used, in particular the surface code that I spoke of, is based on topological ideas. And that can be ported to whatever your favorite hardware platform is.
Okay, thanks. We still have some time for questions, so please come up.
Hi. You told about getting quantum advantage is classically hard. There has not been any big revolution in algorithm side after maybe factorization problem by SOR. Do you have any prediction of when next big revolution or next big algorithm will be found? Because we don't see new protocols or algorithms being made recently in the software or in the algorithm side.
Well, I'm not going to make a prediction about that. I mean, I think that There have been significant advances in quantum algorithms in the last few years, but admittedly nothing as shocking and surprising as Shor's algorithm was at the time it was discovered. The main point I was making is that as the history of classical computing has shown, there are likely to be applications of quantum computing that we just don't have the ability to anticipate until we build the machines at scale and start to use them. So I'm optimistic that as the technology advances and, in the not too distant future, we can run fault-tolerant computations on many logical qubits, then we will be discovering new applications that were not anticipated.
Thank you.
Thanks. Is there one more then?
That was almost exactly my question, but
Okay.
that's crazy. Along those lines, though, thinking about how there haven't really been as many quantum algorithms as groundbreaking as Shor's since he discovered it. Do you have any guesses as to why that might be? Is there something about factoring integers that is inherent to quantum mechanics and some type of deep relation? Or do you think there simply needs to be more time?
Well, Shor's algorithm turned out to be adapting this advantage that I described, where you can get different computational paths to interfere in a setting which it was a problem that people had independent reasons for being interested in the answer. And there are other problems like that, which are number theoretic or mathematical in character, for which similar ideas work. It also made use of the quantum Fourier transform, which is still an important tool in quantum algorithm development. But I actually think of the ideas that we currently know about concerning how quantum computing can be used, the ones which will have the greatest impact on society in the future are the applications to simulating quantum matter, which will advance science, but I think also give rise to technologies that we're not able to predict.
Thank you. Great. Thank you, John. Let's thank John again.
Thanks.
So I would now like to introduce Michelle Simmons, who's the Sienta Professor of Quantum Physics in the Faculty of Sciences at University of New South Wales in Sydney, Australia. And over the past quarter century, she's established and led a large and world-leading effort dedicated to the fabrication of atomic-scale devices in silicon and germanium using the atomic precision of scanning tunneling microscopy. And in that context, she's created atomically precise devices in silicon, pioneered the first working, quote, perfect single-atom transistor, and the narrowest conducting doped wires in silicon. So, Michelle? Okay, so our next speaker is Ramamoorthy Ramesh, Purnendu Chatterjee Chair in Energy Technologies in the Material Science Department at UC Berkeley. So Ramesh has made seminal contributions to the science and technology of epitaxially grown complex correlated oxides, solving, for example, a 30-year-old fundamental problem of polarization fatigue. And he's also demonstrated electric field control of magnetism using multiferroics to control, to enable attojoule magnetoelectronic devices. One of the amazing things about Ramesh is that he's also played very prominent leadership roles at the national level and has a really big perspective on the big problems that need to be solved. So, Ramesh.
Thank you, Nitin. Can you all hear me? Maya, can you hear me? Okay, very good. All right, so thank you for the chance to speak. This is an amazing symposium. Let's thank the Kavli Foundation, who are our sponsors. There they are. Thank you so much for supporting science in turbulent times. Yes, indeed. Yes, thank you for, under turbulent times, science around the world, not just in the United States, everywhere. So like Nitin mentioned, I'm going to start with a different perspective. You heard two fantastic talks from Michelle and John. I'm going to take you through a different pathway. How does one think about solving big problems, but using fundamental science? That's kind of our game plan for today. Acknowledge a few people. There are two people I want to acknowledge. One is Dr. Hussain. He's been teaching me spin transport. He came from Albert Furt's group in Thales, and he's been a fantastic addition in my group. The other one is my daughter. She's a PhD student and my close collaborator. This is a lot of fun, I can tell you. We argue a lot about this and that, but it's a lot of fun, and I hope it'll last for a long time. So thank you, Maya. And of course, in the United States, as like everybody else, the funding agencies, we've been very fortunate to work with a lot of funding agencies who support our work. The one person I should talk about is, I have to point here, this guy, Mani Patuni. It'll come up in a few minutes, the context for Kepler Computing, which is a company we started to really look at quantum materials. Okay, I want to go back 60 years. This is an important slide. It talks about the moonshot. Anybody know what the moonshot was? Yes, of course. Yeah, all you guys know this. That's right. Yeah, for immigrants like me, this is bar none my most favorite president, President Kennedy. Very charismatic. And he had amazing speechwriters, people who could really, evoke a lot of emotions. This was the speech that he gave at Rice University in 1962, 12th of September, 1962. And this called a nation to arms, bring the best ideas. This was in response to another, not a crisis, but a global challenge. This was the challenge from the Sputnik program, the Soyuz program, Yuri Gagarin going into space in 1957. And so this was the launch of the Apollo program, a very formal launch of the Apollo program. But you can read the language, just fantastic. And I've listened to this speech maybe about 1,000 times. The reason I did that was because we fast forward now to 2010, launch of something called the Sunshot Initiative. This was the first Obama administration, and at that time, things were very romantic. Both the Senate and the House were Democratic, and the White House was also Democratic, so they could do a lot of things. Steve Chu was the energy secretary. He's a dear friend of ours. And so Steve was saying, we need to go green, we need to go green. And so here's what the challenge was. The challenge was back in 2010, the price of solar electricity was about 30 cents a kilowatt hour. Poor public university professors could not afford that, very simply. I tried to do it, it was very expensive. Okay. You look at the other technologies, for example, coal, other technology, natural gas, nuclear, they were much lower. So the challenge was, how do you take something at 30 cents a kilowatt hour and bring it down to 5 cents? The 5 cents I'm going to get to in a second. 75% reduction in the cost of a technology, which is a commodity. And people at that time, back in 2010, said, you guys in California are smoking. We said, yeah, maybe, but there is no law which said you cannot bring the price of this technology down. It just had to be innovated through. And there we learned a lot of things about innovation. What's the role of innovation in pushing this cost down, the sense of urgency, the notion of parity. The 5 cent number was approximately a market parity number. When you're working in a commodity, or the computing stuff is not, which we'll get to in a second, when you're working in a commodity environment, price really matters, cost really matters. Okay. So we will get back to this parity number in a few minutes again. If you look at what happened to the price of solar, it's gone from about 30 cents back in 2010 to about 3 cents. You can go get wholesale agreements for solar well below 3 cents a kilowatt hour. So solar, our biggest goal was to take the technology out of politics and put it into the hands of the customer. The state of Texas is the biggest deployer of solar in the nation. Who would have thought that? And that's all because, not because of Sunshot, I was the director of the Sunshot, but we didn't do everything. We basically awoke an entire bunch of people. China did all the manufacturing. We brought down the cost of financing and all of those things. So solar is now very pervasive, but that's not the end of the story. Fast forward to 2020. This was my second tour of duty in the administration. I was part of the Biden-Harris transition team. When you go from a Republican to a Democratic administration, you have a transition team which makes sure that you move seamlessly. I was on the energy team, and they said, hey, you ran Sunshot, why don't you start to think about the big problems? These were called the Earth shots because sun was done, moon was done. We said, let's focus on the Earth. Okay. So we identified a set of topics, and that's going to be our segue point. The first one was very obvious. Solar had nothing to do about solar energy. It had to do with energy storage because of the variability of the source of energy. So long duration grid scale storage, it's about $10 to $30 a kilowatt hour. Tesla Gigafactory is $150 a kilowatt hour. Carbon shot had to do with direct air capture. The fundamental science there had to do with entropy of mixing. How do you overcome the entropy of mixing at a cost structure of about $70 a ton? Today, that's about $500 a ton. Hydrogen shot was saying, can you create hydrogen, just creation of hydrogen, at about 50 cents a kilogram? It's about $5. So you could see all of them had a cost target to hit. That is effectively the parity number after which the market will take over. The home shot was a very tough one. We argued a lot in our team. How do you reduce energy consumption by a factor of 3 in the built environment? It's a macro system, but how do you think about this problem? And the fifth one is where we had fierce discussions. Arun Majumdar at Stanford, he was the chair of our team, and he was saying, what are you talking about? This is a very small amount of energy in computing. But way back in 2014, we had done some calculations, very simple, which said if AI, machine learning, IoT go up exponentially, it is quite possible that this scenario will change. So we said this has to be a national initiative on energy efficient computing. How does one bring the computing energy down to an attojoule per operation? So one of the big things I put in front of you all is not only to think about the speed, the density, but also the energy in the computing process. Computing in the era of AI macro chips, super chips, it's no more kilowatts of energy being dissipated. It's megawatts of energy being dissipated in these super chips. And these are going to be all over, whether we like it or not. That genie has left the building. I don't think any political person can stop AI, which is great. I think it needs to go push technology. If you look at the markets, for example, exponential growth is being predicted by Deloitte, by other market search firms. Everybody is talking about this market becoming a few $1 trillion by 2030, growing about 15% annually. And so this is not a very, very small market anymore. It's growing very rapidly. So then you say, I start from the macroscopic economic, techno-economic perspective. How do I go all the way to spin-orbit coupling, the fundamentals of condensed matter physics, and see if I can make a connection? Ideally, I would like to write down a Hamiltonian which does that. That's probably preposterous at this point, so we will just have a general feel for this. This was the slide I was talking about. Way back in 2014, we had done this calculation that we said if it's business as usual for semiconductor electronics, approximately 10, 20, 50 picojoules per operation at that time, then an exponential growth in the energy will show this red curve. And we said, we really need to work very hard to bring that down to a manageable number. So our goal was, can I take beyond CMOS down to an attojoule per operation, which is not impossible, but requires a lot of innovation. Now, the energy consumption at this point is about 8% of compute energy, or about 20% of primary energy. We'll get to that in a second. This was analysis in 2014, and in 2020, we were having fierce yelling matches in our transition team because we could not agree with each other. Fortunately for Ramesh, the Semiconductor Research Corporation put out their decadal report. This figure was the most important figure. This is all of the semiconductor companies telling us that this is growing exponentially, which you see in the green curve. The growth of the energy production is approximately linear, about 1 to 2% annually. So the conclusion from here was that by 2030, 8% of electrical energy is approximately 20% of primary energy, assuming that that primary energy is coming from fossil fuels, God forbid, but that's still the game that we're playing. There's a conversion factor of about 40%. So Arun Majumdar backed off. He said, okay, go ahead, write this report. And we wrote a report which said the United States really needs to pay attention for 3 reasons. Computing is at the core of our national security. Computing is a competitive issue worldwide. And the most important from my perspective is that computing energy, that nexus is incredibly important. If you buy that argument, then we say, what can we do about it? As physics people, as material scientists, engineers, we think a new physical phenomenon is required. And if you look back into history, this is a plot from Intel. This fellow used to work at Intel. It's a plot from Intel going back to these 2 fine gentlemen, the birth of semiconductor electronics, bipolar technology. That's a heat output in these technologies. By the time we got to the 70s, it was clear that bipolar was just too energy inefficient. That led to CMOS, these 2 fine gentlemen, and that has essentially the same trajectory. So the message here is that we need another 1000x improvement in our energy efficiency. The question is, what's the pathway? And our hypothesis is that quantum materials, where not only the charge of the electron, but the entire degrees of freedom, the spin, the charge, the spin-orbit coupling, all of them will play a role. In the next 15 minutes or so, that's what I'm going to try to convince you. So we have gone from economics to energy. Now we're going to cascade down slowly, step by step. If you look at the left side of this picture, that gives you a schematic of the standard CMOS transistor, and the KT log 10 divided by the charge equals 60 millivolts. That comes from Boltzmann distribution function. It's also in electrical engineering language, that's called the Boltzmann tyranny, because that's a limit that you cannot cross in this classical computing model. Typically, it is not 60, it's more like 80 millivolts because your manufacturing is not at the limit. So the question is, can I go from nkt log 2, n being the number of electrons that you have in your system, and you apply a field and align them, that's how the transistor works. The question is, can I go from nkt log 2 to simply kt log 2? And there is a possible pathway where you use the intrinsic order, intrinsic interactions, quantum mechanical interaction like the exchange interaction, for example. And you can create a double-well structure system. A magnet is a good example. A ferroelectric is a good example. We will talk a little bit about multiferroic materials in just a second. So we said, if I have to mimic computing, I would go back to the human system, neuromorphic computing, where both logic and memory operations are done together. Today, in this computer, that logic chip is manufactured somewhere. The memory chip is manufactured somewhere, you put it together. Most of the energy loss is simply going back and forth. So we said, why can't we use a simple double-well structure, which is the basis for your memory, and do logic with that? And that's the story I want to tell you. And in doing so, we want to make computing 1000x more energy efficient again. So fast forward to 2016, we were working with the folks at Intel, this group, and they came up with a very interesting design. They said, we have looked at 25 different classical computing approaches. We think using a ferroelectric or a multiferroic is one of the most efficient ways to do it. So in this particular device, you have an input, which is a voltage. This blue layer is a magnetoelectric layer. You apply a voltage, change the magnetization direction. You do your compute, and then you have to read it out as a voltage signal. Reading out a charge signal is much more easier than reading out a spin signal. So this requires some innovation. Okay, the biggest learning for somebody like me 10, 15 years ago, 12 years ago, was that voltage equals energy. That's sounds trivial, because if you're an electrical engineer or a physicist, 1/2 CV squared for a capacitor. And therefore, the entire focus is how do you bring down the voltage of operation down to about 100 millivolts. And the 100 millivolts was a number that we came up with by saying, if I get to 100 millivolts for certain classes of materials, you're going to get to about an attojoule per operation. So that's a number that we're going to look at. For switching ferroelectric or a multiferroic at 100 millivolts, we're not very far off. We're very close. For reading out a spin signal as a charge signal, so using the so-called inverse spin Hall effect, back in 2016, we had no clue how to do this. The data at that time was saying we could do it at maybe 50 to 100 nanovolts, and we needed 100 millivolts. So the question is, how does one innovate for that? But there are many pathways to do this. Depending on what your persuasion is, you could take different approaches. What I'm showing you is one possible approach for this. Okay. Why electric field control of magnetism? That itself is an interesting question. If you look at this data, these are all various technologies in various stages of evolution. All of them are using a current to switch a magnet. And you could see that the energy density is way high, maybe 3-4 orders of magnitude higher than what you would like to have. We would like to get to about somewhere here, which is an attojoule or 1 microjoule per centimeter squared. So many of these current-based approaches will not be energy efficient. That's the big conclusion. The other big learning for me especially was that if you go back to your physics textbooks, and you look at how do you create a magnetic field of, say, 6 Tesla. This comes from colossal magnetoresistance. You need a current of about 30 amps to do that. If you're a physicist, 6 Tesla is a small number, about 8 Kelvin. If you're an engineer, you jump out the window because that breaks your bank. So the energy consumption in this is a really important point. And whether you have a nanocrystal or a millimeter crystal, it's always 6 Tesla. Electric field, on the other hand, if I have a 100 nanometer thick crystal, electric field is only about 4 volts electric potential to give you 400 kilovolts per centimeter. So if you're in small scale dimensions, electric field is always better. And finally, it's fun and challenging because you really have to be careful about paying attention to all the details. Okay, magnetism and ferroelectricity. A lot of you have seen these kinds of systems before, a lot of sessions at this meeting. Perovskites are a good platform. Lead titanate is the poster child for that. The typical electronic structure is that there are no d electrons. Otherwise, this system would have some conduction. On the other hand, if you look at these perovskites, the so-called colossal magnetoresistive materials, they have electrons. They have double exchange in them. And so the question was, can you mix 2 of them to get to a material which is both magnetic and which has polar order? And this material, bismuth iron oxide, is the poster child for that. It is a good ferroelectric. It's also a good antiferromagnet. Okay, now some quick information on the system. It's a very robust ferroelectric material that by itself is useful to make products. It also has some very fantastic magnetic structure. These are called the spin cycloids because of something called the Dzyaloshinskii-Moria coupling. The spins cycloid around. And so you could see these in NV magnetometry, very fascinating structures. Then, fast forward again, you can then look at the local magnetic structure. The cycloids are going up and down the chevron patterns. You can apply an electric field to the ferroelectric structure underneath, and then you can switch the polarization, and the magnetization also changes. So you can do all of these. It's now very well established that you can switch the magnetization with an electric field. A little bit more macroscopic scale, you can create a GMR spin valve on top of the multiferroic, apply an electric field, and switch its magnetic state back and forth at the scale of about 0.5 volt. The question is, can we get to much lower values of 100 millivolts? Getting to 100 millivolts is going to require this community to innovate a lot. Because we're now talking about materials that are a few nanometers, maybe 3 to 5 nanometers in thickness, 5, 10, 15 unit cells of the material. How does one grow them? How do you understand the role of defects? How do you measure the properties? All of them are important. We have gone down to about 200 millivolts. That's the best that we have so far. Getting to 100 millivolts means we have to pay attention to all of these. Now let's look at the meso structure that we proposed, the one we show before with the Intel people. It was a nice structure, but it was before the time where we understood how to probe an antiferromagnet. The next couple of slides will explain this some more. We were saying, is it possible to create a transistor-like structure where I have a gate which is modulating the multiferroic or the antiferromagnet? How does one go about doing this? What are the physics questions? What are the device questions? That brings us back to this fine gentleman, antiferromagnets. In his Nobel lecture, Professor Neal said, it looks like it's very fascinating, but I don't see any use for them. I mean, what we now know is that antiferromagnets are going to be fantastically useful. They can be very, very useful. Okay. So I'm not going to spend much time on the details of antiferromagnets, but what we will talk about are these spins which are moving around, the so-called magnons. Those are quantization of the spins in the antiferromagnet. But the key difference is that the velocities of these magnons can be significantly larger than in a ferromagnet. 30 kilometers per second versus 1 kilometer per second. The frequencies go from gigahertz to terahertz. So those are very useful practically. This paper, I think, changed the entire perspective of antiferromagnets. This happened after we wrote the meso paper. What this was saying is, hey, if I have an antiferromagnet like iron oxide, I could sense the magnetic state by simply measuring the spin transport through this. And they simply put a metal here, another metal, a spin orbit metal, and they simply ran some spin current through the antiferromagnet and probed it. We said, that's interesting. That's how you do the measurement. You have a spin orbit metal like platinum, and you sense it on the other side. We picked up on this a little bit later in 2021. We said, hey, bismuth ferrite is an antiferromagnet. We should be able to do exactly the same. And this is exactly what we saw, that we could indeed get to a hysteresis in the spin Hall voltage, probing the antiferromagnetic order as a function of electric field, which is on this axis. But the unfortunate problem was we were getting outputs of the order of 100 nanovolts, not 100 millivolts. So the question was, how does one get to those higher values? One could use the Seebeck effect or the spin Hall effect, and this equation turns out is important. It relates the spin current, Js, to the charge current through the spin Hall angle. Going forward, that becomes an engineering manifestation. How does one optimize that? So we said, okay, let's go back to the drawing board. And this slide is perhaps important because, at least for us, it's giving us a blueprint as to how to go about doing this. We know that we need perfect interfaces. Epitaxy is a very important part of it. We need confined magnons, which I'll show you in a second. That's Maya's and Sajid's big contribution. We think we need to minimize scattering because you don't want the spins to go all over. How to manipulate the quantum materials part of it using the spin orbit coupling matrix elements. That's really where the quantum part of it really plays a big role. So we have a whole bunch of different approaches, making perfect interfaces, enhance the spin transport by magnon confinement, and so on. So a simple way to look at this magnon confinement is by looking at a fiber optic cable. This is a huge industry, but it's based on one simple physics idea of total internal reflection. You could see that the light is bouncing back and forth because the refractive index of the core is slightly larger than the cladding. And so light is simply able to go back and forth. Now we said, can we do something like that with the spins, where the spins are just going through one layer? This is where Maya's work comes in. She's an MBE grower, and she showed us that she could grow atomically precise layers of these materials. This layer is an antiferromagnet with different properties compared to bismuth ferrite. These are 13 unit cells, precisely 13 unit cells. And she can go back and forth and change the number of unit cells. So this looks like a confined structure. That's a chemical map of the structure. So the picture on the right side shows schematically how the magnon confinement happens in this system. And there's work that this guy did, who was a postdoc at Berkeley 20 years ago, who showed that the difference in the magnetic anisotropy plays a key role. Okay, now here's an important piece of data which convinced me to come back from research administration, go back to the lab. If you look at these hysteresis, these are the inverse spin Hall voltage as a function of applied field. And you can see it's not nanovolts anymore. It's going to about 5 to 7 microvolts. Still not millivolts, but microvolts. Pure BFO is basically in the noise. And if you look at it as a function of the thickness, you see very strong confinement of effects on the spin transport. So it's telling you that indeed you can start to play games with how the spins are transported in the structure. The last piece of my discussion before we finish up, this really has to go back to the basics of quantum materials. If you look at the spin conductivity, sigma, it has this term, which is this omega, which is a spin-Berry curvature. You're really going back to the fundamentals of condensed matter physics in these systems. That has two terms. The numerator is the spin orbit matrix elements, which really comes from the atomic numbers, basically. It goes as the atomic number. And degenerate electron bands, this is where quantum materials are really coming to the fore. So you can start to now design these materials. You can tune the crystal field or the spin orbit coupling through the chemical species. Replace ruthenium with iridium, you get very different spin orbit coupling. Iridium is very strong spin orbit coupling. Or you can take the same structure, you can squeeze them, you can stretch them with epitaxy, and you can break symmetry in the system. You have so many degrees of freedom. Strontium iridium oxide is a wonderful material. There are sessions around the APS meeting focused just on this material. It has this perovskite structure, but it also has very interesting electronic band structure relevant to what we're talking about. What is also interesting is that when you squeeze it or when you stretch it with epitaxy, you can take a material that's orthorhombic, different crystal symmetry, and you can make it change its symmetry. That impacts the spin transport significantly. And if you look at the electronic structure of this, you can see it has all of the features that we're looking for. These kinds of band crossings which are essential for enhancing the spin transport. And you can see that the spin conductivity is indeed very large for the system. There is a whole host of materials that, including what our chair has been working on for 20 years. He's one of the pioneers in this business. Now with strontium iridide, we do know that as I reduce the thickness of the layers, these are in unit cells, go down to a few unit cells, we have very strong efficiency change in the spin to charge conversion. So which is really valuable for us. This is kind of the culmination. This is a broad spectrum of various kinds of material. The spin Hall angle is our measurement vehicle. There's a whole bunch of materials primarily clustered around this area. Bismuth selenide is supposed to be a material which has a huge spin Hall angle. There are a lot of debates going on in this field. Barium bismuth, lead bismuth oxide, one of the old high TC materials, has a very large spin Hall angle as well. There's a whole bunch of materials that we can now start to tap into. But the strategies for these are essentially the definitions of quantum materials. You want non-symmorphic symmetries to enable band crossing, topological insulators, strong spin orbit coupling, Weil and Dirac semi-metals with nearly degenerate bands, essentially manipulating electronic structure. So, converging on this, antiferromagnetic spintronics. I showed you data at 100 nanovolts. How does one go from 100 nanovolts to 100 millivolts? One way is to make single domain materials. You take care of all of the small scale things. We get to 500 nanovolts. You go to these exotic topological materials, you get to 2 microvolts. And then you go to these magnon confined structures, you can go to 100 microvolts. And the question is there a pathway? We do believe there are pathways to go to 100 millivolts. One way is to go to a vertical structure. When you go take the same material, strontium iridide with bismuth ferrite, you can get a millivolt. You can take these magnon confined structures, you can get to 10 millivolts. That's our state of the art as of this morning. we can get to, credibly, 10 millivolts of output voltage. So we have gone from something which is at 100 nanovolts up by 5 orders of magnitude in the output voltage. We need to get up by 1 more order of voltage. What do you think? We can do it or not? Yeah, exactly. Yeah, if you believe President Obama, yes, we can do it. Yeah, right. So the question, we can bring it all together. We started back in the early 2000s with ferromagnetic metals going to oxide ferromagnets. And then this antiferromagnetic work by Lebrun and his team was just a big landmark in the learning process. And we have gone all the way up to about 10 millivolts. And we are hoping in the next few months we will figure out a pathway to 100 millivolts. So quantum materials are no more the materials of the future. They are the materials of the present. This is a 300 millimeter wafer. This is where my friend Sashi Manipatruni, this is from Kepler Computing, where they're actually making these. You're actually productizing this. And like Michelle was a fantastic talk. Like Michelle is doing making products. We are now taking quantum materials and making products out of them. But the secret in all of this is you have to keep innovating. You have to keep going at it. This community is perhaps best located for that. So, Nitin, I will stop with a video that I prepared for you guys. We got a consultant. So you can go from global economics, identify a problem area. This is AI and machine learning, a systems level. And then say, look, I need to get to energy efficient electronics. You don't have to stop at the circuit level or the device level. You can go all the way down to new materials. In our case, we're going to say quantum materials are a big part of it. New materials which have all these exotic properties. And you can go all the way down to spin orbit coupling, use that spin orbit coupling, tune that spin orbit coupling, and enable this new set of computing technologies. So with that, I will stop and take questions.
Thank you, Ramesh, for that infectious enthusiasm and a grand.
By the way, I don't have COVID, okay?
It's a great reminder that there are serious challenges that need to be overcome in conventional computing.
Exactly.
And that quantum materials, that we may not be dealing with entanglement and coherence and so on in this particular form of quantum science and technology, but it plays a critical role, right? I mean, the quantum nature plays a critical role.
Absolutely.
Okay, so we have time for questions.
Hi, thank you for the great talk. I'm a graduate student from Yale University. I'm working on quantum materials research every day. And but I have a question, like more of a general question. So my naive take of kind of why now quantum materials is still not replacing this silicon electronics is mainly because 2 reasons. The first one is many of them are belongs to a strongly correlated regime, and as you said, it's even hard to write the Hamiltonian, so we kind of still cannot understand the whole physics inside it. So making us we don't know what should we make for these new materials, right?
Yeah.
And then the second challenge is many of these synthesis is very challenging. As you mentioned, MBE, we need ultra high vacuum, and the speed is slow, and kind of it's very hard to get mass production. So I want to ask from your take, what do you think it's kind of where will be the breakthroughs happening along these 2 lines, and kind of what will be the timeline for us to really kind of have this new quantum materials to really make human lives better?
Yeah, by the way, you captured, I want to have this as the background to answer your question. The first thing, I'm going to first put my engineer hat on, and then we'll turn it around and use the physics hat on. The engineering part of it is, if you look at quantum materials, we as a community have not made a serious attempt to scale it. If the basis is silicon-based electronics, that's what this is, right? You have to be able to scale the process. We have done small crystals in pulse laser deposition, which is what we do. It's all 5 millimeters, 10 millimeters. You have to be able to scale it because you actually have to make a product which has two attributes for sure, which functions the way it should function, and it's robust. That's what the customer will pay for. So in order to do that, you have to do it at a scale where you can actually demonstrate that all these technologies work, that the quantum mechanics that you're putting into it actually works. That's happening. This picture is a reminder to say, yes, that is happening now. It's taken us a while because we had to figure out, how do you deposit a material like bismuth ferrite? How do you deposit bismuth selenide? Nitin can do it by MBE. Can you scale MBE to 300 millimeters? The answer is absolutely yes, if you want. You have enough money, of course. But you can go buy an MBE system which does 300 millimeter process, which means you can run it through the entire product development cycle. In terms of the fundamental understanding, I think we as a community have done very well. Margaret is going to talk about probes. How do I really probe all of the properties or exotic properties of these systems? I mean, we use some relatively simple things like ferroelectric measurements or spin transport measurements. There's a lot to be done in that dimension. So you're going to see a lot of progress. But my bet, which is I'm a co-founder of Kepler, my bet is that the time is now for these technologies, these ideas to become real technologies so that you can actually start to productize them. Keep in mind, just to finish this, keep in mind, even if you make the product, there's no guarantee you're going to make money. I always keep saying this. When you write a Nature paper, that's actually a very broad Gaussian because it's just a set of ideas. When you go to advanced development, that Gaussian becomes sharper and sharper. By the time you go to a real product and you make money, that's a delta function. It's only some of those ideas will actually become a product. And that's the secret. I mean, Michelle is doing a fantastic job. John's company is doing a fantastic job in the quantum. A Kepler kind of people are trying to do the same with digital computing, but using quantum materials. Sorry.
Okay. Yeah. And just a quick comment to the student asking about MBE and so on. So techniques such as Michelle's, which need ultra-high vacuum, or MBE, I mean, MBE is already a production scale manufacturing in the semiconductor optoelectronics industry. So it's not, it depends on what you want to do with it, right? And eventually it's a question of, your method and will it make money or not.
Exactly.
Okay, so I think we need to move on. So let's thank Ramesh again.
Thank you very much, guys.
Thanks very much. Okay, so our next speaker, Margaret Murnane, is Distinguished Professor of Physics at the University of Colorado. She's made seminal contributions to the science and development of high harmonic processes for tabletop sources of intense coherent X-rays and is regarded as one of the founders of attosecond science. And these advances have really led to fundamental discoveries in areas ranging from basic atomic and chemical dynamics to materials dynamics to nanoimaging. So we're going to hear from her about how one uses this advanced laser technologies to generate coherent, intense X-rays.
Thank you so much, Nitin. Is the microphone working okay?
Maybe not.
Yes, thanks, David. Thanks so much, Nitin, Jonathan, and the Kavli Foundation. I very much appreciate being part of this symposium to talk about how do we build the quantum microscopes of the future and how in this process we've gone from Star Wars to sculpting the radiating electron wave function. Or another title would be the quest for the ultimate light-based microscope. And Dr. Ramesh has made a very good case for why we need better ability to characterize materials and characterize the quantum nature of materials. And before I go into my talk, I also wanted to acknowledge group members who are here at this APS Global Summit meeting. Drew, Emma, Martin, Eric, Chenier, Yanhao, Gabriella, Jai, Ethan, Wilhelm, and then collaborators John Yao and Henry Captain. Okay, so we just heard a wonderful and inspiring talk, why we need to design better nano devices. And this is very challenging even with current generation technologies. We need to understand and integrate materials with and know their thermal, mechanical, structural and magnetic properties. But at the nanoscale, all of these properties are very different from bulk properties, and we don't have great ways of measuring them. So we need better, not only microscopes, but we need functional microscopes. And this problem is only getting harder. Traditionally, when we talk about function, for example, heat transport, people measure that process using visible lasers. And you can do that. You can use a micron scale ruler to look at a nanoscale process if you have a good model of what the phonons are doing. The problem is we don't have very good models of what phonons are doing. So in many cases, there's no way to validate our understanding, which makes a predictive design very challenging. And as we heard from the talks today, the problem is only getting harder as we try to make atomically perfect interfaces and also measure other properties, including the coherence, transport, topology. It becomes very challenging. Okay, let's hope this works a little better. Good. Okay, I can hear it's working better. And although we can make really stunning images with the subatomic precision using techniques such as cryo-electron microscopies, and we all remember those beautiful images of viruses and vaccines. To make those images, we have to freeze a device or a cell to make sure that when bonds are broken, the structure isn't destroyed. And so what we would really like to develop are microscopes where we could take a functioning nano device and look at heat, charge, or spin moving through that device in 3D, or in the case of a biological system, image a cell, but be able to zoom into image dynamics at a molecular level. Now, X-rays or short wavelength light in general have always been a very attractive way to do this. The wavelength is very well matched to nanoscale processes, and in addition, we get inherent contrast. We know what the chemistry is, what the element is, what the magnetic state is by just looking at the X-ray spectrum. On top of that, because the photon energies, particularly in the extreme UV region of the spectrum, the photon energies are relatively low. The photoelectrons we generate are very low energy, and so they don't destroy the device. So you can put, for example, a polymer into an extreme UV microscope, image it multiple times, you don't break any bonds, so the structure is preserved. And if you have coherence, then the waves can be focused both in time and space to get nanometer spatial resolution and temporal and femtosecond temporal resolution. The problem until very recently was that generating coherent beams at short wavelengths was extremely challenging. And that's because the usual way we do this is to use a laser. That's what gives us directed beams in space, which is the spatial coherence, or pulses in time, which is the temporal coherence. But to make a short wavelength laser, the power scaling is extremely tough. The power scales, the required power scales as the wavelength to the inverse fifth power. And so what that means is that I can hold a laser in the visible and powered by a small battery, but if I try to make a laser at 1 nanometer, it's going to take a terawatt of power. And that's on order of the electrical generating capacity of the United States. So we are not going to make a 1 nanometer X-ray laser or a 1 angstrom X-ray laser. It's just not possible. And that's why in the 1980s, during Star Wars, there were some serious proposals to make X-ray lasers by detonating a nuclear weapon in space. And it's also why
the first coherent X-ray laser was demonstrated using an entirely different technology, beautiful accelerator technology. This is a picture of the X-ray free electron laser in the Stanford campus. It's absolutely beautiful and generating stunning new science. But the scale here is on order of a few kilometers. And Dr. Ramesh also sort of reminded me that Steve Chu was Secretary of Energy when the XFEL came online. And of course, and this was also the 50th anniversary of the demonstration of the laser. So in Washington, DC, Steve gave a wonderful talk where he said, and oh my goodness, it's an amazing device, but it's not free, and I should know it because it costs a couple of $1 billion. So it is great, but it is not going to be adjacent to every fab or used to perfect an interface. It's just not scalable. And so that's why it's very interesting to see how far we can push tabletop sources of short wavelength light. And in this regards, it's actually amazing of how badly we have done, because in almost every area of science, if you think about electron microscopy, think about memory, think about computing, in all those areas, we've gone in the last 60 years, we've increased capacity or scaled by 6 or 7 orders of magnitude. In lasers, and for those of you who are not in the field, it's been quite abysmal. The first ruby laser was demonstrated in 1960, lasing in the red. And the shortest wavelength laser that's in widespread use is the excimer laser at 193 nanometers. And that has a wavelength less than a factor of 4 smaller than the first laser demonstrated. And so that's why some of these, the light source technologies I will talk about are actually quite interesting. They are the only current way that we can scale from the excimer laser into the soft X-ray region in a tabletop setup that one might be able to use in a manufacturing or other materials R&D process. So let me first talk about high harmonic generation that's based on femtosecond lasers. And it turns out that a femtosecond laser with very modest energy, a millijoule of energy, maybe a 20 femtosecond pulse duration, is the best thing we have to pluck or sculpt the quantum wave function in an atom. So you shine the femtosecond laser onto an atom. The electric field is very high, in fact, higher than the field binding the electron to the atom. And so part of the wave function can undergo tunnel ionization. Then it's born in a strong field. It will move away from the ion. And then when the laser field reverses, will go back in a boomerang-like orbit and can convert its kinetic energy into an X-ray. Now, this happens on every half cycle of the driving laser. And so one gets periodic emission in time. And of course, from a Fourier transform, that will give you a periodic emission in spectrum, where each one of these spikes corresponds to adding an odd number of laser photons. Now, the way I've described it, it might be an extreme version of a nonlinear process such as second harmonic generation. In fact, that's not really the best way to think about it. The best way to think about it is that the laser is actually creating a nanoscale quantum dipole antenna from the electron wave function. This movie, you can think about it as the electron in the ground state of hydrogen, irradiated by an intense laser field that creates a beautifully spatially and temporally modulated wave function that looks as if we're modulating the electron with a much higher frequency. And so that's the physical origin of these high order harmonics. It's really, really beautiful quantum physics, but it's a dipole transition. And we all know dipole emission is not directed. So if you want coherence, if you want to make a beam that has a well-defined phase, and if you want to be able to control the temporal properties, then you need to figure out how to add the emission from, it turns out, trillions of atoms. And so you can think about it as needing to add the emission from the same number of atoms as there are people on Earth. So you can think about the laser as a quantum conductor. But the issue is that the conductor has a wavelength of 4 microns, for example, and you're trying to force the emission of light with a wavelength of 1 nanometer to add together coherently. And you know if you want constructive interference, you better line up those waves to a tenth of the wavelength or a tenth of the frequency at least. So that means you're looking for a way to add the X-ray fields from many atoms in phase with sub-angstrom spatial resolution and sub-attosecond temporal resolution. And we have no modulators that can possibly allow us to do this. Nothing responds this quickly. But fortunately, the quantum physics actually helps here because it's a strong field ionization, so the electrons only appear at a specific time during the laser pulse. Their trajectory is very deterministic. So if we take advantage of the quantum physics, we can actually do this. And so it took our community over 20 years to figure out how to do this. And you would think the quantum physics and the sculpting, the dipole would have been harder, but it was harder to figure out how to phase the emission because we went to different conferences. So the Division of Laser Science people would go to the DLS conferences, and the AMO people would go to the atomic physics conferences. And of course, we all know that we're so involved that it takes a while for the laser people to understand quantum and for the quantum people to understand laser science. But we figured it out eventually as a community. And the reason it was hard to understand is think about how we do second harmonic generation. We use a crystal where we're taking advantage of birefringence, and that allows light of different colors to travel at the same speed. With X-rays, their photon energy is far above the resonances. So they are going to travel happily at the speed of light in vacuum in pretty much anything you put them in. But laser light doesn't do that. The laser light driving the process will tend to slow down in a gas and speed up in a vacuum. So it took a while to figure out that phase matching happens in time, that the leading edge of the laser pulse is traveling too slow, the trailing edge travels too fast, but the center of the laser pulse travels at the same speed as the generated X-rays, and that's what allows coherent addition. So essentially, eventually our community figured out that what we had was actually a coherent version of the Röntgen X-ray tube. Because think about what happens and of course that's by far the most widespread X-ray technology that's in use. You know, think about an X-ray tube, you boil electrons off a filament, accelerate, and then hit an anode, and then you get radiation. Well, think about high harmonic generation. You pluck electrons from the ground state of an atom, you accelerate it in a coherent laser field, and then you recombine with the part of the wave function that's not ionized, and you do that all in a phased array. And so it essentially is a coherent version of the X-ray tube. And when I want to tease my laser colleagues, I tell them that when we add in selection rules and other quantum properties, that we can actually control X-ray light better than we can control visible light. I'm doing that a little bit in a tongue-in-cheek fashion. For example, just by changing the color, we can make an X-ray, the color of the driving laser, we can make an X-ray supercontinuum or a single frequency. We can, just by changing polarization and orbital angular momentum, we can make a light pulse that changes in shape during the pulse. We can change the polarization, and this is probably the most complex waveform that anybody has generated, where the laser pulse on a sub-femtosecond time scale is changing in polarization and frequency and time. Can make pulses shorter than anything in our natural universe, with the exception of electron-electron scattering. So before I talk about some of the quantum properties that we've been able to measure using coherent short-wavelength light, I'd like to share some exciting advances in expanding the spectrum into new regions, and in particular, the vacuum UV region of the spectrum. All enabled by these beautiful photonic fibers that I'll explain in a moment. In particular, the vacuum UV region is very important for our March meeting audience. We can use it for time and angle resolved photo emission, for combustion, fuels, hypersonics. And on Tuesday, we had some beautiful talks at the symposium on the nuclear referenced clocks. And it's a very exciting area right now. And all three of these applications need tunable vacuum UV light with the ability to control the spectrum, because you want to look at one particular molecule or one particular band in a material. Or in the case of nuclear referenced optical clocks, you want to look at one particular transition in the thorium nucleus. So this is a very nice summary of the nuclear transitions and the transitions for optical clocks. So in blue here showed the transitions, the nuclear isomer transitions. Most of them are at an MeV, very hard for us to access. But there is one transition in the thorium-229 nucleus that happens at 8.4 eV. And that's a very nice place that people can reach with high harmonic generation, and with other approaches. And one very nice thing is that the thorium can be doped into, for example, calcium fluoride crystal. And so now you have the advantage of having a nuclear transition that may be insensitive to the environment, and many atoms in a solid state target. So there's a lot of motivation for developing compact light sources that could address this and help develop the technology. Of course, you would like it for timing and navigation, but also for more fundamental questions, such as, can we make better event horizon telescopes, for example? The beautiful picture of the supermassive black hole, the Messier 87, that was done with 1.3 millimeter light. What if we could take that down by 3 orders of magnitude by using these nuclear reference clocks? And so that would be one potential application. The initial research in this area was done in Germany and at UCLA and at Jula. It used techniques such as high harmonic generation, which is wonderful for some applications, but not particularly in the vacuum UV. It takes way too much energy. More recently, we've figured out ways of making cascaded processes, but they also are not very efficient, on order of between 10 to the minus 5 and 10 to the minus 6 efficiencies. But very recently, we figured out that by doing a 4-wave mixing process, we can generate light from blue into the vacuum UV with macroscopic conversion efficiencies for the first time. And this has allowed us, we think, to make the first measurement of VUV laser light on a power meter, on a thermal power meter. So one critical technology advance that made this possible are called anti-resonant hollow core fibers. So Dr. Ramesh talked about optical fibers that are guided by total internal reflection. If we want to use the center of a fiber to do nonlinear optics in a gas to enhance the nonlinearity, because gases are not as nice as crystals, they're not as strong as crystals for nonlinear conversion, then we need to put gas inside a hollow fiber. The guiding of light by glancing incidence reflection in a fiber is nowhere near as efficient as through total internal reflection, but through the advances in photonic crystal fibers, they can put hollow fibers within a hollow fiber. This essentially acts as a high reflection coating. They were developed, one of the motivations for developing them was for high frequency trading. It turns out light travels faster if you're in air than if you're in glass. And there they would have propagation over kilometers. We only need crystals about this long to be able to get very nice VUV sources. And so we can get 10 milliwatts of power in very narrow line widths. This is not narrow enough for a clock, but by adding a frequency comb, this does get you to the right region. And not only that, but you can phase match multiple processes just by changing the pressure. And so for applications such as RPs, this 11 EV line is a very nice capability. Okay, so let me give just a couple of examples of how we use coherent short wavelength light to try to better understand quantum many-body physics or develop microscopes where we can image spin textures in 3D, for example. Also have a lot of work on understanding nanoscale. Heat flow or phonons do not behave in nanoscale materials, do not behave like they do in the bulk, but I really don't have time to talk about today. So how do we make a better microscope? So think about all the really advanced microscopes that you might use in your research, if it's a TEM or other types, nano-enhanced, tip-enhanced microscopes. None of them these days yield direct images. One always has to take the data output, combine it with the image outputs, combine it with a computational toolbox, and that's how we generate, for example, images of the COVID vaccine or 3D spin textures or X-ray microscopes that can work at the diffraction or theoretical limit. So why has it taken so long? So in the visible, we can buy beautiful, perfect lenses and make a perfect visible microscope. In the X-ray region, that's not possible. Nothing refracts X-ray, so you have to use diffractive optics, and they're limited by your ability to fabricate. So most traditional X-ray microscopes based on an image-forming lens are 10 times, at least 10 times worse than the theoretical limit. But if we have coherence, we can get around that. And in fact, it has allowed us and a much broader community to make, for example, short wavelength microscopes that can work below the wavelength limit. So how do they work? So if one has a coherent beam, one can shine it on an object, for example, a cell. The light will scatter from the object, and instead of using a lens to form an image, one can just collect the scattered light on a detector, and then with the right protocols and algorithms, one can actually use a phase retrieval algorithm to make an image of the object. This was first proposed way back in '52 and was demonstrated in 1999. David Serre was a co-author on both papers. And this was David's full paper in 1952. And for the young people in the audience, I love this final sentence. The extension to 3 dimensions is obvious. None of us would get away with that right now if we put that in any of our papers. And of course, phase retrieval algorithms, you have to constrain how you take the data for them to be robust. But a big advance in this field was made when John Rodenberg and others proposed, well, just scan the beam, have overlap between your scan positions, and now you have redundant data and it stops the algorithm stagnating. So now you can force the microscope to yield a good image of one sample. And now we've got stroboscopic X-rays, microscopes that are perfect ways of collecting the electronic structure, the magnetic structure, the elastic properties, mechanical properties, and transport properties. Now we're beginning to have microscopes that can really tell you about what is the material that you made, how can you make it better, how does it work, how can we see quantum things. Of course, none of us can do that alone. In our group, we just work with others to try to demonstrate these new types of microscopes. In fact, nobody comes to us who wants a fast image because we have to design a new microscope. But as just a simple example, imaging polymer metamaterials is hard because if you put them in an SEM, the high energy electrons will break bonds and the polymer will change its shape and you don't know what you made. But with these lower energy extreme UV photons, then we have a way to image metamaterial and not destroy it. And of course, that's also of interest for imaging live biological samples. Just thought I would show just one picture of how big these systems are. In the extreme UV, they're relatively large. You need a femtosecond laser and then these little conversion devices that hold the waveguide and pressurize things. This is a picture of a system at EMEC. EMEC is a large nanoelectronics research institute in Belgium where many of the semiconductor companies do their research. This is a system that CAM Labs, which is a spin-off company, installed at EMEC. And then just what's interesting here is they set up this materials R&D facility like a mini beamline. So here they have RPs, all these different spectroscopies so they can, for example, figure out how to integrate 2D and topological and other novel materials, try to develop the next generation of resists that might work with high NA lithography, exploratory litho, and other things. Now, I know I'm almost out of time, and I don't have the ability to do anything except I'm going to move like this. So, with quantum speed, and yes, and in the last minute, just talk about a fun topic. Eric Thang, who's in the audience, presented this in a talk Monday morning at 8:30 a.m., so I will bet that not many of you saw his talk. But it is the challenge of how to image spin texture in 3D, ideally stroboscopically, but for now we were happy enough to do it statically. Dr. Ramesh also talked about the beautiful DMI interactions that can host these different types of spin textures, some of which have been seen, some have not yet been seen. They're very hard to measure because if you have a material with a spin texture, mostly they only have magnetic contrast and X-ray scattering from spins is not very efficient. So this was an experiment we did since we're still developing tabletop soft X-ray sources. We did this at the Advanced Light Source Synchrotron at Berkeley. The folks we were working with, beamline scientists, didn't think it was going to work because you only have magnetic contrast, all kinds of stray light issues. But eventually we were able to do it. This is a picture of the iron gadolinium multilayer sample. We had to fib holes in it because if you only have magnetic contrast and you don't understand what your spin texture is, you need something to tomographically align your 3D images. So after 3 years of developing new algorithms and developing the right measurement, we were able to make, well, Eric and Iona were able to make these beautiful 3D images. These are actual images of both the charge contrast, which is just the material, and the spin contrast. And they can also analyze these skyrmions and show that they have a preferred helicity, we believe, due to the asymmetry between the bottom and the top of the sample. And we can compare with micromagnetic simulations, look through each skyrmion in 3D and show that as theorists had predicted for these types of dipole stabilized skyrmions, that they had indeed nail types, tops, and block centers. And then, since there's been so much beautiful talk in this session by Michelle, Dr. Ramesh, and I know David also, that we really need to know surfaces and interfaces with atomic precision. All the algorithms I talked about are also applicable to electron tachography. So for looking at how in a twisted 2D Moiré superlattice, does that make the material into waves? And Jian Miao is a person who's pioneered this. It's the same Jian Miao that was on that 1999 paper that did the first diffractive image, but now he has a whole series of beautiful discoveries of nanomaterial phases. For example, understanding why the magnetic strength of certain materials was less than people thought, because it turns out it's because even a nanoparticle can have multiple phases, not all of which might be magnetically hard. So with that, I'd like to thank Nitin, Jonathan, Kavli Foundation, and you for your attention, and thank my collaborators for the joy of doing science.
Thank you, Margaret. That's that's really quite a technology that you've developed, and I know it's
there's a lot of people.
Right, you and your team, and I know how hard it's been, pushing the boundaries of that. So thanks. Questions from the audience? So I was curious, a lot of the data that you've shown on the skyrmions and so on, so these are measurements done at room temperature, presumably?
Yes, and that was just because at the time on that beamline we used, there was not an ability to cool. That is changing over time as the beamlines are updated.
But are there any constraints in terms of going to low temperatures in probing?
Well, okay. The image I showed of the skyrmions, that was, so thank you for the question, Nitin. It was 108,000 images.
Okay.
So this is not how we want to look at one of Dr. Ramesh's devices. Instead, what you would want to do is structure the light to detect the magnetic texture you would want and not have to do a full D tomographic reconstruction. That would put one in a much better position to be able to use a cryo-cooled holder, and then also not have to do the full reconstruction. We did it as a way, because to understand, you still need to be able to calibrate, you still need to be able to see if the 2D structure one inferred is correct. So we wanted some way of calibrating a dynamic measurement versus a static.
Okay. Question here.
Thank you very much for the exciting talk and the new technology development. So in principle, you need longer wavelengths to generate higher harmonics, right?
Yes.
So what is the current state of art of the shortest harmonics you can generate?
So the shortest harmonics are just above a kV. And the reason I wasn't showing the image of the skyrmions with that technology is the femtosecond laser technology at 3 microns is 30 years behind the titanium sapphire or ytterbium technology that can be used to generate VUV or EUV light. And so it was purely a laser development with a small market. So, and so when it's done in academia, it takes quite a while. And think about, the applications of femtosecond lasers are mostly in cutting or in surface processing and such. And high harmonics require a very particular kind of femtosecond laser. And so it took quite a while to do that development.
Thank you. And in principle, is there any physical limitation how long the longer wavelengths you can go or how high the harmonics can go?
So nobody can answer that question right now, because if you wanted to try to get to, let's say, being able to take a medical X-ray with, with a coherent beam, you would have to couple time-dependent Schrodinger with Maxwell, with huge differences in the driving laser wavelength and the generated X-rays, and it's computationally not possible. So right now what our field is doing is sort of devising approximations and taking baby steps experimentally, and then theoretically once we have data to validate. But it's a nice situation. Nobody knows where the limit is.
Maybe one very quick last question, because we have
fascinating. So just what is the next, is there a goal for the next 5-10 years, something similar to the quantum computation, people having a error-corrected quantum computer, for example? So is there a long-term goal like that? This is the...
Yeah. So this is, okay, so think about lasers when they were developed in the 1960s. There's a great interview where Walter Cronkite is interviewing, oh God, what am I am spacing out. He was interviewing, thank you, Henry, Awschalom. And Walter says, so Art, what are we going to do with these lasers? And Art took out a potato and he had the ruby laser and he pulled the trigger and showed Walter Cronkite that there was a perfect white spot where the skin of the potato had been. And Frito-Lay now uses lasers to peel the potatoes for their potato chips. Now, I am not saying that the X-ray lasers, will follow that path. What I'm saying is lasers are a tool, and there has been no widely accessible short-wave lasers, and they're just coming out now. So clocks, RPs, hypersonics, combustion, fuel development, all of those are relatively, they're very, very hard technically, but they could be done with the vacuum UV technology that could fit on, a shoebox. And so you have a much better chance with the technology that is small, or Michelle showed she had a rack-mountable solution for people who wanted to use her technology. It's a little harder in the EUV. You saw that picture of the system at EMEC. That takes an optical table. So it's just a little bit higher barrier to ownership, and you need space. So it will be exciting.
Great. So thanks, Mark. Let's thank Margaret again. So we come to our final speaker for tonight, David Awschalom, who is the Liu Family Professor at the Preskill School of Molecular Engineering at University of Chicago. So David has made many pioneering discoveries in condensed matter physics, particularly in the context of spin dynamics in semiconductors. His group made the first observation of long-lived spin coherence in semiconductors and launched the field of semiconductor spintronics. This has also played a big role in the development of spin qubits in semiconductors. In recent years, he's really advanced the frontiers of quantum spintronics through the discovery of new platforms for defect-based spin qubits in semiconductors. And he's also played a big role at the state and national levels in advancing quantum science and technology. So, David?
Thanks, and thanks very much for inviting me. Thank you for the APS and Kavli for being up here today, and thank you all for staying here till the bitter end. Well, maybe not the bitter end, but the end. And one of the things that struck me in hearing all of the talks today is how every speaker had a connection with industry, either launching their own company or working tightly with them. And that's one of the things I'd like to talk about today in the next 20 or 25 minutes, which is how partnerships with industry accelerate science. particularly in a field that's so new that industry is so keen on looking where the discoveries will be, because as John pointed out in the very beginning, it's impossible to know where the biggest impacts of this field will be. And I love the example of the ARPANET project in the late 1969s, where a group of scientists got together and thought, well, maybe we should connect 2 or 3 computers in the state of California. And in December, they got the program managers together to review the results of their projects, and they sat down, they typed the letters LO, and the system crashed. So I would say a very realistic program management experience for some of us. About an hour later, they rebooted the system, they got it going, and they sent the first message, login. And I would argue at that time, in 1969, they would have had no concept of how this basic science project would have changed the world that we live in today. And when we look today, 2 zettabytes of information are transmitted on the internet. That's 2 billion terabytes of information. 25 billion connected devices on the planet. More devices than people living on the planet. Commerce, $1 trillion of commerce last year alone, with billions of websites. And again, who would have imagined this at the time where people were just thinking about the basic issues of connecting information across long distances? So here we are with quantum information in a similar way, and you've seen some historical photographs earlier in some of the presentations, but I really love this one, because when you think about a 30-ton computer, it's a pretty significant object, right, in the 1940s. And when people thought about portable storage, I love this example, which you can see in the Computer Museum in California, the IBM 350 system, 5 megabyte disk drive. So this was a 110 storage device of just 5 megabytes. And in today's dollars, IBM leased that at $35,000 a month. So huge change in technology. And now we look at Intel, 800 quadrillion transistors are being shipped every year, right? And you think about what's in your iPhone 17, for example, almost 20 billion transistors, with actually just about 40 watts of power. Just extraordinary developments in maybe 5 to 6 decades. And so all of us are saying, what happens if you push this to the ultimate limit? A single particle, a single atom, a single electron, a single nuclear spin, what will happen? And to really push that, one of the great things about physics, of course, is we can explore the fundamental interactions, as we heard about today, and when we look at how industry is viewing this onto the science world, they're beginning to see opportunities in all of these different areas of spaces. Remarkable, and I would argue some of these have just appeared in the last few years based on discoveries that have happened in people's laboratories. So let's look into some of those. I'd like to focus on just a couple of domains in the last 25 minutes or so here this afternoon, and to start with semiconductors. Where it's difficult to argue the fact that the numbers of devices produced per second, the number of transistors shipped all over the world is an extraordinary thing. We've become adept at manipulating silicon unlike any other material on the planet. And the challenge now is, how can we control individual electrons, individual nuclei, and atoms at the quantum mechanical level? So something that both Michelle and John were talking about earlier. And as an atomic engineer, or say a quantum engineer, which I think many of you are going to be, it's a remarkably rich landscape. We heard from Ramesh about the importance of materials, how a quantum state can be controlled by the lattice, right? How the electronic state itself can be manipulated either independently, the role of phonons and magnons, mechanical control, all sorts of ways you can play with these different degrees of freedom. How you create the quantum state becomes an opportunity, but also a challenge, and how you might mitigate damage and decoherence. And the applications that are emerging, whether it's sensing or commuting or communication, each of these applications will feed back on these other issues and say, what system do you choose? How do you mitigate the noise? How do you control quantum coherence in matter? And to what end? Why are you even doing this in the first place? So I want to pick a couple examples because I think they're both historically interesting, but also showed a lot of scientific surprises just in the last year or two. And in the semiconductor world, one of the materials that has been studied for a very long time is diamond. And it's been studied by companies like GE, laboratories like the Naval Research Lab in Washington, and at the time they were interested in removing defects from this material because diamond is arguably one of the best thermal conductors on the planet. So people were really interested in diamond for microelectronics. And they developed NMR techniques and ESR techniques to look for these defects to remove them. Now, ironically, in the quantum field, we're putting the defects back into the diamond because a missing atom in a lattice, like here, this missing carbon atom and a nearby nitrogen atom with the dangling bonds, creates a spin triplet state in a very wide bandgap material, which means it can operate at very high temperatures. And nature has provided in this defect a really beautiful two-level system, because by just illuminating a defective diamond with a pulse of unpolarized laser light, you generate a spin-polarized electron, because its excited electronic state relaxes through some metastable levels into a spin-polarized ground state. And nature's also been pretty kind. Because of strain in these materials, you lift the normal degeneracy of these spin states, and in the absence of a magnetic field, can address them and drive Rabi oscillations between spin up and spin down with microwaves. And in materials like diamond, these microwaves are at about 2.8 gigahertz, and that's the frequency for your cell phone. Very easy to apply these fields, just a wire will do it, and it's quite effective. Because there's a dopant nearby like nitrogen, you might think that's sort of an annoyance, but nitrogen has a nuclear spin. So it's a single atom memory. And groups have shown that you can move this electronic qubit into the nuclear spin and back, shuttling the wave function in both directions to store information, and shows a proof of concept you can build a single atom, both qubit and memory, in a solid state system. And this operates, by the way, at room temperature. So this got the community thinking quite a bit. Diamond is great, but diamond is actually a tricky material to use because diamond grows on diamond. You can't dope diamond both P and N type. So while it's a very interesting physical to explore, there are challenges for scaling it. So this is where the physics comes in. You begin to say, can you do a type of genetic screening? Can you use advanced theoretical techniques, pushing density functional theory, and other electronic methods to see if you can do a screening to look for other materials in the world where you could actually look at this physics, but do much more with it. Play with the environment, as I showed in that earlier slide, in a much more flexible way. And we launched some of these efforts with Chris van de Walle and some other theorists in Santa Barbara over a decade ago. And the results of this produced these series of materials you can see on this left side. And the thing that's interesting about these materials is they're all commercial. You could buy all of these online. And I circled the top one because that's the one that struck us as the most exciting, silicon carbide. So how many people here have heard of silicon carbide? 4 people. It's so sad. This is the APS meeting. What's wrong with you? So like silicon carbide, I hate to tell you, it's the most popular material on the planet. It's used in solid state lighting. It's used in electric vehicles. I'm guessing all of you own silicon carbide. If you have a light bulb at home, that's an LED. And as an experimentalist, something that Nit and I commiserate about a lot, the price of a wafer like that and a piece of diamond are the same. So this is a pretty exciting development. You can N and P-type dope it. You can buy lasers and transistors with it. So it offers a very rich science landscape to integrate quantum interactions in a very controllable material. And I'm going to talk a little bit about another material, cerium oxide. And I'm guessing very few of, I won't embarrass the group, but I'm guessing very few of you have heard of cerium oxide. It's very commonly used in semiconductor electronics because it's a great dielectric system. It's something that they use to separate layers during transistor growth. But as a physicist, if you look at cerium oxide, this is pretty exciting because it has virtually no nuclear spins in that material. So now you have a landscape you can explore quantum technologies without having to isotopically purify anything. So I want to show you some recent developments where, again, moving with industry, identifying materials through theory through a co-design approach, and trying to ask some more fundamental physics questions. What limits coherence? What is the source of quantum noise at the level of single particles? These are questions you can address when you have the flexibility to play with a landscape. So what about silicon carbide? These theoretical predictions were exactly on target. And I'm just giving you a snapshot of some of the data that comes out of measurements from commercial wafers of this material. On the left, you can see 1 electron qubit that you can control very nicely in a commercial wafer. Next to it is a single nuclear spin, silicon-29. Again, you can move information from the electron to the nuclear spin, drive Rabi oscillations, and have beautiful quantum control. And these are materials that are used from 5G technology, as I said, to lighting, to satellite communications. Most aircraft use silicon carbide instead of silicon because it operates at high temperature. So it's turned out this is a very, very interesting thing, and you can now entangle these electron and nuclear spins quite reliably with about 90% fidelity. And if you look at this density matrix on the right, this is an experimental result showing the integrity of the electron-nuclear spin combination with thousands of entangled pairs. So I like this example because it shows with some insight from industry, using this as a platform to ask some very interesting science questions, you can learn quite a bit. And these are projects that we've been doing recently with both HRL and with Toyota. And during the question session, if you're interested, I'm happy to explain why Toyota would be interested in quantum states. So now, as I said, you can go a little farther and ask, what is it that really limits coherence in matter? And one of the things that we were exploring is you can look at both electronic noise and nuclear noise in a quantum system like this, but suppose now you take a material like silicon carbide and you just make an LED. You just put a pair of gates on it as a way to try and remove electronic noise from the magnetic system in a material that's isotopically purified now, and ask yourself, what limits coherence for both the electron spin and the nuclear spin? This is a snapshot of some data in sort of a politically correct landscape of red and blue to show single-shot measurements of one nucleus in silicon-29 seeing quantum fluctuations. And this is in the presence of sweeping out random electrons in the system, so the gate is on. And if you look at the T1 times here, it's over 3 hours. You've now made very long-lived quantum states in a commercial system. Now, a surprising piece of science that came out of this is if you look at these purple and blue curves on the right side of the screen, it'd be these single-shot measurements, you can see a very long difference in the nuclear lifetime. The only difference is the initial direction of the electron spin, where the hyperfine interaction is transferring the wave function to the nucleus. Whether they're co-aligned or whether they're anti-aligned, the lifetimes vary orders of magnitude. It turns out when you anti-align these spins using the hyperfine interaction, you freeze that nuclear spin, making it oblivious to the fluctuations around it. That makes these coherent lifetimes well over 30 minutes now. And in some of these systems, we'll leave there a couple of hours. So we believe these are some of the longest lifetimes measured in any quantum system, whether they're atoms, superconductors, or semiconductors. And I wanted to show this, not because the lifetimes are so long, but it shows the richness of new science that comes out through these partnerships, trying to understand more deeply what systems are at your disposal to ask some very fundamental questions. I mentioned cerium oxide. I just want to flash one screen. Again, it's a material that is interesting because there are no nuclear spins effectively in it. And the prediction was if you dope the system with erbium, that's your defect. Erbium is a rare earth system where one of the nuclear spin levels, the ground state, emits light right into telecom. So not only is this an interesting quantum system with no nuclear spins, but you can send the qubit information through optical fibers, much like Margaret was just talking about, in modern optical fibers with relatively low loss, and send these flying qubits from one location to another as a means to instigate long-distance entanglement. So these measurements were just started. It turns out that actually they do work very well. This, again, was a prediction through density functional theory, a collaboration with Subrata Guha and Jiefei Zhang at Argonne National Laboratories. And the data is really quite nice. These were very dense systems of erbium, just to see if a signal came out. And even these very dense systems, both the spin lifetimes and the coherence lifetimes are very respectable. So again, I think these partnerships take us into very interesting directions. And that brings me to the second topic I wanted to mention. Suppose you had never seen a semiconductor, and somebody asks you, I want you to make 1 billion identical qubits reproducibly, inexpensively. I'm arguing, with the exception of the beautiful STM techniques that we heard, and I have no financial investment in your company yet. We'll talk at the break. You might say, well, it's a really crazy idea to take a block of silicon and carve it into atomically perfect states. What you would probably say, and I'm guessing the students would say this in the audience, why don't we just grow them like a chia pet? Although I'm guessing none of the students actually know what a chia pet is. You're going to grow from the bottom up using molecular tools. with over 100 years of chemistry, where chemists have become remarkably adept at designing molecular systems with specific stoichiometries at very high volumes. The reason this is very attractive to us is now you have a very flexible, atomically engineerable landscape that's tunable, meaning you can choose the electronic interactions and strengths you want. It's portable, you can pick these up, you can move them around, and they're scalable, using systems like organometallic frameworks, where, again, for decades, chemists have made large-scale arrays of beautifully crafted systems. So I think this is a nice example for the APS and to the Kavli Foundation, the importance of foundations. When we proposed this work, it was very hard to get it funded. I'm not bitter, I'm just saying it was hard to get it funded. I am bitter, actually, but it got funded. Anyway, after a few years and quite a lot of failure and some extraordinary students who stuck with this project, it worked beautifully. And the goal was to effectively make a semiconductor through molecular design. So if I handed you this sample in the lab as a student and you thought it was a semiconductor of the type we've heard about today, things would be exactly the same. It's just the synthesis is different. And the example I'm showing here was, I would say, the first optically controlled spin qubit. It was made with Dana Friedman as a collaboration when she was at Northwestern, and now she's at MIT. And this looks exactly like the energy diagrams I showed you of Diamond. You excite the system the same way, you measure it the same way, but this is an example of the power of quantum engineering in a system like this. The only difference between these three curves you see on the green is that one ligand, one methyl group, is moved over one unit. It's atomic engineering. And the difference is the quantum operational frequency, instead of being limited by what nature gives you, say in Diamond, that 2.8 gigahertz, you can make it 3, 1, 5, whatever you'd like it to be. You can design your qubit frequency from first principles and build it scalably. The reason this is exciting is that we heard a bit about superconducting qubits. They typically run around 5 gigahertz. If you wanted to match a spin qubit to a superconducting qubit, you design it for 5 gigahertz, and you can do this. So it's an exciting development in the field, which I believe in the next decade you're going to see a lot of development. A more recent example that came out at the end of last year was some work with Leah Weiss and Grant Smith. Grant just spoke about this at the March meeting, was to make a quantum memory. Same idea. This was a collaboration with Jeff Long's group out at Berkeley to take erbium, a very popular rare earth memory, but make it chemically. And I won't go into the great details here. It works at telecom. The surprising science that came out of this is that the line widths of this memory and the coherent properties are as good or better than any semiconductor. It's something we would have never guessed when this project began, but it's an extremely exciting development of building new classes of quantum systems, again, with a calculable architecture. And as John mentioned, small molecular systems can be simulated now on quantum machines to some degree. So I think working together using quantum computing, with quantum theory, with molecular synthesis, will lead to rapid advances in this field. The last example I want to give is, again, something that was funded by the Moore Foundation, which was when you push this to the level of molecules and think about sensing, one of the challenges of quantum sensing is how do you get the sensor close to your target? Because that's where quantum mechanics plays its strongest role. If the quantum sensor is far away, it's not obvious that you win quite a bit and take advantage of the quantum aspects of your sensor. So in biological systems or in chemical systems, this is hard to do because if you make semiconductor particles small, maybe 20 nanometers or 30 nanometers, the fact is the surface tends to decohere the quantum state, and even if it doesn't, you're still pretty far away. So the idea came up is, could you take a molecule, say a protein, right, where something could be shielded inside the protein? Proteins are very small. Could you make a quantum bit out of a protein? After all, it's a molecule. And we proposed taking a very common protein, which is a yellow fluorescent protein. It's used in biological imaging quite often, and as a physicist who admittedly knows very little biology, well, no biology, it was very attractive to me because it looked like a chemical system, emitted light, and had a multi-level system. So I just wanted to mention this because at the end of the day, it actually worked quite beautifully. It allowed us to be able to build what we believe is the first protein qubits. Not only do they operate at room temperature, but they can put inside living cells, and this is an example of one that actually in a human kidney cell. And you can do quantum sensing of magnetic fields, electric fields, temperature under ambient conditions. The exciting direction about this is that these proteins are built in the cell. So instead of trying to place the protein externally or your quantum sensor from the outside world where you want, why not let nature build a quantum sensor for you? And in things like fusion proteins, have the protein genetically engineered to attach to the target you're seeking. So I wanted to say this because I think another example of working with industry, understanding where their challenges are in quantum sensing, and using some interesting physics insight to attack some new problems with some new methods will really advance different parts of this field. And this is work done in collaboration with Peter Maurer at Chicago and Julie Galli and Laura Gagliardi, who helped develop the theoretical aspects of this. So where is all of this going? And as John was saying earlier, it's very dangerous to predict anything. But I don't know if any of you suffered problems getting to the March meeting because of weather. Yeah. So you may have been stuck in the airport. This is O'Hare. I'm guessing many of you have had no problems with O'Hare. Really? Okay. But it's an interesting example of where industry is looking at opportunities of quantum information science. And Boeing, for example, has come to us quite a bit saying, we're really interested in optimization. And one of the things we began to appreciate is the impact of this on them. A 787 has over 2.5 million parts. So one of the challenges that companies face is, how do you know the most efficient way to build an airplane on day one? They don't. It takes them dozens of planes before they understand how to solve this problem. But imagine economically if they could do this properly on day one and how it would affect the supply chain. The next thing you think about at the airport is, I'm guessing probably none of you have ever waited for a plane. I've waited for a plane a lot. How do you assign a plane to a gate? I know all of you know this math, 5 planes and 10 gates are 100,000 options. O'Hare has thousands of flights and a few hundred gates. This is a very tough problem for an airline to optimize. It's one of the reasons United, for example, has started working with IBM to try and look for possible algorithms to help them with this problem. It's a growing obstacle for them. Fraud is another area, of course, so quantum information, quantum encryption is something that people have been thinking a lot about, and industry is wrestling with the fact that over last year, for example, there was $12 billion in consumer fraud, over $250 million credit card stolen just last year, and it's an exponential increase. So they're worried about that. And finally, navigation is an increasingly important problem. I don't know how many of you follow this, but the amount of GPS spoofing that's happening in the last year has also been growing exponentially. That number is old. There were about 2,000 spoofing attacks on pilots in commercial flights last year, people pretending to be satellites. So it's not obvious where the impacts are going to be, but it's become increasingly clear where there may be roles for quantum information science and technology. And you can see it at the March meeting. We heard in some of the talks this afternoon some of the impacts that are happening with error correction, for example, that was mentioned, Boeing's quantum navigation project, the partnership with Cisco and IBM now to develop protocols for quantum communication. And as several of the speakers mentioned, the financial impact. And you can see that just in the equipment show upstairs. It's extraordinary how this show has changed from just a few years ago. So I want to spend the last few minutes talking about how we thought about that. I was very fortunate to move from California to Chicago with the idea of building one of the first quantum science and engineering programs. And there, the idea was to try and blur the normal distinctions between academic departments, national laboratories, and companies. Remove these distinctions and think about a collaboration where the research is done very tightly together to understand where are the targets for science, educate industry about these developments, because let's face it, most companies don't know a lot about what's going on in this field, and we need to impedance match with them. And we've grown now to a few hundred researchers, 7 institutions. You can see them on the bottom of the screen around the Midwest region of the country, some international partnerships, and now actually over 60 corporate partners that span the globe. And we've learned so much science from our company partners. We're watching these sorts of changes happening at the federal and state level. I know many of you know about the National Quantum Initiative Act that launched national centers in 2018. The renewal for that is still sitting in the US Congress. The Reauthorization Act, where that amount of money has been proposed to double. In one of the rare moments of bipartisanship in this moment, can I say that? It's too late, I just said it. Rare moments of bipartisanship, it has 100% endorsement on both sides of the aisle. So it's a measure of how important people find this field to be right now. Illinois has been rather unusual, diving in very deeply with over $700 million of investment from the state, both in new laboratories for industry, university, joint research projects, but also the Illinois Quantum and Microelectronics Park, which was the home of defunct steel mills and steel fab about 10, 15 minutes south of Chicago, where the old USX Steel plant was, and now is a site which is hosting over half a dozen quantum companies and more growing from around the world, actually coming in there. It is a bit sobering. I don't expect anybody to read the font on here. I've really tried to make this larger, but if you look at the colors, these colors represent countries that have national quantum programs. It's extraordinary how this has become a global effort. And I'm not picking out any country, and I realized that, Michelle, now Australia, it's on the map. I just didn't highlight it. Don't shoot the messenger. But I did highlight programs that have well over $1 billion investment in their national quantum programs. And what's exciting about this is you can see the global, right, investments. It's not just one or two countries, it's spread everywhere. It's incredibly important to realize the power of international interactions and collaborations in moving this field forward. It's extraordinary, and some of these countries might surprise you. Japan, for example, just tripled its budget for quantum science and technology. Collaboration is incredibly important, and one of our biggest supporters in driving this is industry. They know it as much, if not more than we do, how really important it is to have international collaboration. But it also raises something that all of us can think about dealing in the pre-competitive stage we're working in right now in science and technology. How do we balance competition and collaboration? And how do we do this early on? It's inarguably true that the US workforce is international. And it's inarguably true we have to bring the very best and very brightest students here into the United States to help us. There have been models that have worked very well in the past, like Semitech, right, where the electronics industry around the world work together, and they're still working together. Semitech is still around after 30 years of trying to work on technology challenges together, even though they compete fiercely in their products. So I wanted to mention that this is something we raised a few years ago, both in Washington and both with law schools around the country. And a document was just produced with the law school at the University of Chicago, driven largely by a law firm, Barnes & Thornburg. It's an international law firm, and it's called the Quantum Law Navigator. If any of you are interested in this, it's a very interesting document to read. It's about 100 pages, but there's a short executive summary in the beginning. How do startup companies deal with international issues in export control? How do they develop international partnerships? And how do they do things in a way that will make them successful? For all the startup companies who've been hearing about in the presentations tonight, as well as you're seeing about in the equipment show, this is really important. And so this is a free download for people to get advice on what to do. At the risk, this is being recorded? Okay. At the risk of disturbing any large companies, I think it's true that most innovation in new fields happens with startups. And it's important to help startups. And so we worked very hard on building the first quantum accelerator in the nation to fund startup companies, make sure their business plans are successful, working with the Booth School of Business, and make sure that they can do what they need to do. And I want to end in the last slide or two with the workforce. And I know this is something that people at universities talk about, but I'm not sure everybody here appreciates that over 70% of the quantum jobs that are predicted to happen in this field are people without graduate degrees. This is pretty important to think about. We've had independent groups give us estimates in the Midwest of what these jobs would be. And in the next decade, it's expected that over 800,000 jobs will be generated in the quantum field, with about 200,000 in the Midwest. So it's really important that we make this connection to community colleges, to training programs, to associate degrees. Or as one large company recently told us, the last thing we want is more people like you. Really? Meaning me, not you. Okay, so let me end here. I think we are, as you heard from most of the speakers today, at a really remarkable moment. We're at the birth of a fundamentally exciting new technology. You will be the ones driving it, so this is exciting, I think, for all of you. How we balance these issues from privacy and security and collaboration will ultimately drive these fields. It's a really early day. We need a very creative and diverse workforce. I'm very confident that we're going to get there. So thank you very much.
Thanks, David, for that really terrific perspective that covers everything from the exciting fundamental science to the big picture. It's great. So, questions from the audience? So while they're thinking, just a quick question about some of the defects that you were talking about, right? So with the molecular systems, for example, there are certain molecular systems where you can observe the qubit coherence and so on at room temperature, and others only at low temperature, right? So there are general principles that are at play.
Yeah. So there are, and what I think is this is where theory will play a big role. For example, in straining some of these systems, it turns out you can dramatically increase the operational temperature. So understanding how phonons and these spaces interact, I'm quite optimistic in these molecular systems where you have a lot of tuning in the phonon spectra will advance the operational temperature.
Okay, great. Question here?
Yeah.
Thank you very much for the nice talk. In one of your last slide, the one with the map, with the different country with the over a billion investment.
I was worried about that. Yeah.
It's sad to notice that there are countries that are in gray area without colors. Yeah,
That's
so
correct.
maybe like suggestion for industry here present or like future development that maybe quantum computing could think also a way to make this country get to have a color and not stay in the gray area. Maybe you can comment on this.
I agree with you. I think it's a huge opportunity to do that. And we're seeing it, for example, in projects that the APS has been involved with, like the synchrotron in Africa, right, as a way to do both great science and technology development. So I agree. This is a completely open ground now, and I hope that happens.
Thank you.
Jonathan?
Yeah, so I'm John Bagger from APS. APS is remaking itself, I think, opening its aperture from PhDs, academia, only to a much broader community. What would be the role of APS? How could APS help this broadening that you're talking about?
Yeah, so that's a wonderful question. And my normal response to that is it would be great for the APS to go to the provosts and the presidents of these community colleges and ask them that question. Because with all due respect to many of us, I'm not sure we're the best people to answer that. So it'd be a little arrogant of me to do it. But the one thing that I've noticed when I've spoken to people in Chicago, in the inner city schools and the community colleges, they have no resources for any of this. And their biggest problem, honestly, there are two big problems. One is they have no one to teach the material. So helping there would be incredibly valuable, even if there were ways for graduate students to be engaged, right, through stipends to help with this. The other is literally financial support for the students. So most of the students in these schools are working in order to be in school. They don't have the time to do much of this. So those are the two camps that we see. But I would urge the APS to go to these community colleges. Illinois has the second largest community college system in the nation. So it's an interesting place to start. There are large ones in California and in New York. I would talk to them. And I do think it'd be worth getting a working group together and hear from them.
Thank you.
Thanks.
Yeah.
Yeah, one more question there.
So two questions. One, why is Toyota interested in qubits? Because you mentioned that. And the second question, I think it's a general question to almost everyone here who has seen qubits develop for this long time, is in the long run, would it be the hybrid systems with different hardware platforms talking to each other, or would it be a single system that wins the race? So two questions. Thanks.
Yeah, so just to be clear, if I could answer that well, I would launch a company. I don't believe that anybody has the answer to that one. I mean, I think right now, my own view is that when we look at today's technology, there isn't one system for everything, right? Photonics is doing communication. Until recently, magnetic materials were doing hard drives, and actually still for large data servers, it is magnetic materials who are doing hard drives. Silicon is used, right, for computing and electronics. So if you were to ask that question at that time, I'm not sure they would have said multiple materials and multiple technologies for multiple applications. I mean, that's my own view, but I would argue it's so early to address that properly. It's a research area. I think it's amazing to see what companies have done in scaling up the most mature areas like superconducting technology, which has been around for so many decades. It has a big advantage. But no, I think you'll answer that actually in a decade. No pressure, but I think you will answer it in the years to come. Yes.
There was also a question about Toyota.
Oh, yeah. This is being recorded.
Yes.
Yeah. So Toyota is very interested in a number of things, but one example that they're very passionate about is they view in the next decade or two that people won't be driving anymore. There'll be autonomous vehicles. Any of you taken a Waymo in San Francisco? You should, if you haven't, you should definitely take a Waymo. Did you like it? It's fantastic. So they're worried about a few things, for example. One is what will be precise ways to navigate, right, for a system like that, and they're very interested in systems that don't use GPS. So some of the neat things about the quantum navigation schemes, right, as you probably know, is they use the NOAA maps of the Earth's magnetic field, right, to essentially use the qubits as a compass. And they work very well now. They're really working well, which is pretty exciting. But the second thing is, if you have thousands and thousands of wireless vehicles, you better have a really safe encryption scheme to communicate between them. You don't want anybody hacking into your car, right? So this is one of the reasons they're very interested. How do you build scalable small sensors at the atomic level, right? And how do you develop encryption techniques for communication? And in the longer term, they're thinking about computation as ways to optimize, right, traffic patterns and so on. So that's one of the reasons they're thinking ahead. They know these will be hard problems. But to give you an example, Toyota is one of the biggest users of silicon carbide, for example. And they produce a lot of their own materials for it. So it's quite interesting, right? You might not think that at first. Yeah.
Okay, so let's thank David again for a fantastic talk. And we'll end with Brad Marston coming up to make a few comments.
Thank you, Nitin, and thank you to all of our speakers in this session. What stood out this afternoon was the range of approaches to a shared set of questions, from theory and architecture to atomic scale fabrication, to new tools for seeing and controlling matter, to the realities of translating discoveries beyond the lab. If there's a through line, it's that progress in quantum comes in more than one form. Sometimes it's a clear result. Sometimes it's painstaking engineering. Often it's the work of connecting ideas to systems that can be tested, built, and used. As the Global Physics Summit winds down, I hope that the conversations sparked here continue across the subfields, institutions, and sectors. Thank you again to our speakers and to all of you for being part of the 2026 Global Physics Summit.